Hello there, and welcome to Science for Sleep, a place where curiosity is allowed to slow down, stretch out, and get comfortable before drifting into rest. Tonight, we're settling into a topic that sounds intense at first glance, but reveals itself gently when approached with patience. We're going to talk about charge, not the kind on your phone battery, not the small static shock when you touch a doorknob, but charge pushed all the way to its deepest possible boundary. A place where our equations grow cautious, where language becomes careful, and where the universe itself seems to pause and ask whether it wants to allow us any further. Before we ease into that question, take a moment to notice where you are right now. Maybe you're lying down with the lights already dimmed, or sitting somewhere quiet while the day slowly loosens its grip. Where are you listening from tonight? And what time is it in your part of the world? It's always interesting, isn't it, that a discussion about fundamental limits can be shared across countless time zones, each listener arriving at this moment in their own small slice of the night. If you find this space calming, if the ideas unfold in a way that helps your thoughts soften rather than race, you're welcome to like the video or subscribe. It helps this gentle corner of science reach others who might also be looking for a quieter way to end the day. And now, without rushing, let's begin easing toward the edge of our topic. Electric charge is one of those things we live with constantly without ever really stopping to think about what it is. Lights turn on, screens glow, hearts beat, and signals move through the nervous system, all because charge flows where it's allowed to flow. From a distance, it feels familiar and tame. We learn early that there are positive charges and negative charges, that opposites attract, that like charges repel. It's tidy enough to fit into a classroom diagram, neat arrows pointing inward or outward, little plus and minus signs behaving themselves. But nature rarely stops at the tidy version. Charge, at its core, is not just a property of particles. It's a way matter interacts with the electromagnetic field that fills all of space. When something has charge, it doesn't merely sit there carrying a label. It actively shapes the space around it. Invisible lines of influence stretch outward, telling other charged things how to move, how to respond, how strongly to push or pull. Even when nothing else is nearby, the field is still there, patiently existing, storing energy simply by being distorted. Most of the time, those distortions are small. An electron carries a fixed amount of charge, and even enormous collections of electrons and protons tend to balance out. Nature seems to prefer neutrality. Large objects, like planets and stars, are almost perfectly neutral overall. Any excess charge tends to escape, redistribute, or cancel out long before it grows extreme. It's as if the universe gently nudges things back toward balance whenever they stray too far. Still, physics allows us to imagine pushing charge further. What if we keep adding charge to a region of space? What if we keep packing it in, forcing like charges together despite their mutual repulsion? At first, the resistance is manageable. You need energy, of course, but the equations still behave. The field strength increases, energy density rises, and everything remains, at least mathematically, under control. But only up to a point. There exists a scale in physics that doesn't belong to everyday experience at all. It's not about meters or seconds or volts in any practical sense. It's a boundary built from fundamental constants, numbers that appear again and again whenever we probe the deepest structure of reality. This scale is named after Max Planck, and it marks the regime where our usual descriptions of space, time, energy, and yes, charge, begin to lose their clarity. When we talk about a Planck limit for charge, we're not talking about a number you could measure with an instrument. We're talking about a conceptual boundary, a warning sign in the math that says something important is about to change. At this scale, the energy stored in an electromagnetic field becomes so concentrated that it can no longer be treated as just another field sitting on a passive stage of space. The stage itself starts to respond. This is where things quietly become strange. As charge density increases, the energy associated with the electric field grows rapidly. Energy, as we know, is not just an abstract bookkeeping tool. In Einstein's universe, energy has weight. It curves space. It influences gravity. If you concentrate enough energy into a small enough region, you're no longer just dealing with electromagnetism. Gravity enters the conversation whether you invited it or not. At everyday scales, the gravitational effect of electric fields is so tiny it can be ignored. You could surround yourself with the strongest magnets on Earth and gravity would barely notice. But near the Planck scale, that separation collapses. The energy density of the field becomes comparable to the energy scales where space-time itself becomes flexible, reactive and unstable. What happens then is not something we've ever observed directly. And that's not an accident. As theoretical physicists push their equations toward this limit, they start to see familiar assumptions break down. Space can no longer be treated as smooth. Time stops behaving like a steady parameter ticking quietly in the background. Quantum fluctuations, usually confined to the smaller scales, grow loud enough to interfere with the structure of the field itself. The idea of charge as something neatly attached to particles begins to feel inadequate. Instead, charge becomes inseparable from the vacuum around it. Empty space, which we tend to imagine as nothing at all, turns out to be restless at these scales. Quantum field theory tells us that particle-antiparticle pairs constantly flicker into and out of existence, borrowing energy briefly before disappearing again. Normally this activity is subtle, invisible, averaged out, but under extreme electric fields the vacuum can no longer ignore what's happening. As the field strength increases toward the Planck limit, it can become energetically favourable for the vacuum itself to produce real particles. Electron-positron pairs can be pulled apart before they annihilate, turning stored field energy into matter. This process acts like a release valve. Instead of allowing the field to grow without bound, nature finds a way to convert that energy into something else. In this sense, the universe appears to protect itself. Rather than letting charge pile up indefinitely, it opens new channels. The field discharges itself not through sparks or currents, but through the creation of particles from what once seemed like empty space. The stronger the field becomes, the more efficient this process gets. It's as though the vacuum says, quietly but firmly, this is far enough. And still, the story doesn't end there. Because even particle creation has limits. As we continue to imagine pushing charge closer to its ultimate boundary, gravity becomes impossible to ignore. The energy density becomes so extreme that space-time curvature intensifies dramatically. In some models, the region begins to resemble the conditions near a black hole, not because of mass, but because of energy stored in the field. At this point, our theories stop agreeing with one another. Quantum mechanics insist on probabilities, fluctuations, and discrete interactions. General relativity insists on smooth geometry and continuous curvature. Near the Planck scale, both insist on being right, and neither is willing to yield. The result is a mathematical tension that no existing theory can fully resolve. This is not failure in the usual sense, it's a signal. Whenever physics reaches a boundary like this, it tells us that our current tools are incomplete. Not wrong, just unfinished. The Planck limit is less a wall and more a fog. We can see shapes forming within it, hints of what might lie beyond, but no clear outlines. Charge, which once felt like a simple property, dissolves into something more relational, more dynamic, more entwined with space and time themselves. And this raises a quiet but profound question. Is there truly a maximum charge, or does the concept simply stop making sense beyond a certain point? Perhaps the universe does not enforce a hard limit in the way a battery tops out at 100%. Perhaps instead, it changes the rules so completely that asking about charge in the old way no longer applies. What we do know is this. Every time physicists attempt to construct a scenario where charge reaches the Planck scale, something intervenes, fields destabilize, particles appear, geometry responds. The system refuses to remain simple. It refuses to remain isolated. It insists on becoming something else. This pattern shows up again and again in fundamental physics. Push too hard in one direction, and reality redirects you. Not with violence or drama, but with subtle shifts that prevent extremes from becoming absolute. In this way, the Planck limit feels less like a destination and more like a threshold of transformation. Charge is not just something that flows through wires or clings to particles. At its deepest levels, it is a way the universe organizes influence, energy, and interaction. And when that organization is pushed toward its ultimate edge, the universe responds not by breaking, but by quietly changing the story it tells. We'll keep following that story, slowly, carefully, letting each idea settle before moving on, as we continue toward what really happens when charge approaches the Planck limit. When we hear the word electricity, most of us picture something familiar and comfortably ordinary. A lamp switching on, a phone charging quietly on a bedside table, the faint hum behind the walls that keeps modern life gently awake even when we're trying to fall asleep. Electricity, in that sense, feels domesticated, predictable, something we have learned to expect rather than question. And because it behaves so reliably, we rarely stop to ask what it actually is, or what we mean when we talk about charge as if it were a simple thing that can be stored, moved, or used up. At the level of everyday experience, charge feels almost like a substance, something that can accumulate, flow, and occasionally leak out in the form of a small shock when you touch a metal handle after walking across a carpet. We talk about it as if it were a fluid, even borrowing language from plumbing. Currents flow, resistance slows them down, circuits carry charge from one place to another. None of this language is accidental. It reflects the way charge behaves in many practical situations, and it works well enough that most of us never feel the need to look deeper. But beneath that comfortable picture, charge is not a substance at all. It is not a tiny droplet moving through wires like water through pipes. It is a property, a relationship, a way in which certain pieces of matter interact with a field that fills all of space. When we say something has charge, what we are really saying is that it responds to the electromagnetic field in a particular way, and that it alters that field around it in turn. That idea alone already stretches beyond everyday intuition. We're used to thinking of objects as things that sit in space, separate from their surroundings. But charge does not stay politely inside an object. It reaches outward. The moment a charged particle exists, the space around it changes. Other charged particles, even far away, feel that change instantly through the field. This influence does not require contact. It does not need a wire or a medium. It simply exists as part of the structure of space itself. Still, for most practical purposes, we don't need to think about fields at all. Engineers can design circuits. Electricians can wire buildings. Devices can be built and trusted to work because at everyday scales, charge behaves in a stable and predictable way. Electrons move when pushed. Positive and negative charges attract, like charges repel. Balance is restored quickly when it is disturbed. These rules are so reliable that electricity becomes background noise in our lives, noticed only when it fails. That reliability comes from a quiet fact about nature. Charge, in most environments, does not like to pile up. If too much negative charge gathers in one place, it pushes itself apart. Excess electrons repel one another strongly. They spread out, escape into the air, leak into the ground, or rearrange themselves until the imbalance disappears. Positive charge behaves similarly, though in everyday matter, it is usually locked inside atomic nuclei and less free to move. This constant self-correction is why large objects tend to be electrically neutral. A planet does not carry a significant net charge. Neither does a human body, a tree, or a mountain. Any small imbalance that arises is quickly neutralized by the motion of charges through air, moisture, or surrounding materials. Nature, left to its own devices, prefers neutrality because neutrality is stable, and stability is comforting. When you plug something into a wall outlet, you're not tapping into a reservoir of charge waiting to be emptied. You're creating a path. Electrons already present in the wires respond to an electric field established by a voltage difference. They drift, ever so slowly, passing energy along through interactions rather than racing from the power station to your lamp. The light turns on almost instantly, not because electrons travel fast, but because the field rearranges itself throughout the circuit at nearly the speed of light. This distinction matters, even if we rarely think about it. What flows in an electrical circuit is not charge in the sense of particles travelling long distances, but influence. A coordinated response of charges everywhere in the system. Energy is transferred through the field, nudging electrons locally, passing along a signal that something has changed. So when we think of charge in everyday terms, we are already simplifying. We compress a complex interaction into something manageable, something that behaves well enough for our needs, and that simplification is not a mistake. It is a practical necessity. Without it, we would never have built the electrical world we now depend on. But simplifications have limits. As long as the amounts of charge involved are small, as long as fields are moderate, the everyday picture holds. You can increase voltage, you can store charge on a capacitor, you can generate sparks, arcs, and lightning. All of these are dramatic by human standards, but they remain gentle compared to the extremes allowed by the laws of physics. Lightning, for all its power, is still a modest event in cosmic terms. The electric fields inside a thundercloud are strong enough to tear electrons from atoms and accelerate them through air, but they are nowhere near the point where space itself begins to respond. Even the most intense laboratory fields ever created fall many orders of magnitude short of the regimes where our understanding of charge begins to wobble. And because we live so far from those regimes, our intuition remains comfortable. We come to believe, without ever stating it explicitly, that charge is something you can always add more of, as long as you have enough energy and enough insulation. It feels like a quantity that could, at least in principle, grow without bound. This belief quietly shapes how we imagine the universe. We talk about extreme charges as if they were merely scaled-up versions of ordinary ones, a stronger field, a denser concentration, a more intense version of the same phenomenon. And for a long time, physics encouraged that view. Classical electromagnetism allows you to imagine arbitrarily strong fields. The equations themselves do not protest. They accept any value you care to plug in and calmly return an answer. But equations are not the universe. They are maps, and like all maps, they are drawn with assumptions baked in. Classical electromagnetism assumes that space-time is a fixed stage, unaffected by the drama unfolding upon it. It assumes that fields can grow without changing the nature of space itself. It assumes that energy density, no matter how large, remains just another number. Those assumptions work beautifully at everyday scales. They even work at scales far beyond anything we can touch. But they are not unlimited. The first hint that charge might not be endlessly scalable comes not from electricity itself, but from the relationship between energy and gravity. As charge builds up, so does the energy stored in the electric field. That energy has mass equivalent. It contributes to gravity. It curves space-time, however slightly. At ordinary scales, this effect is negligible. The gravitational pull of an electric field around a charged object is so small it might as well not exist. But gravity, unlike our patience, never stops accumulating. If you keep increasing energy density, gravity eventually demands attention. This is where the comfortable picture of charge as an everyday whisper begins to change its tone. At higher energies, quantum effects also begin to intrude. The vacuum is no longer passive. It becomes active, responsive, unstable in subtle ways. The idea of a clean separation between particles, fields, and empty space starts to blur. Charge, which once seemed like a simple label attached to particles, starts to look more like a manifestation of deeper structures. Even before reaching the most extreme limits, these effects show themselves in small ways. In strong electric fields, virtual particles can be promoted into real ones. In high-energy experiments, charges behave differently depending on the scale at which they are probed. The effective strength of the interaction changes. What we thought was constant turns out to be context-dependent. Still, these are hints rather than revolutions. They whisper rather than shout. They suggest that charge is not a static thing, but a dynamic process shaped by scale, environment, and the structure of the vacuum itself. And this brings us to a subtle but important realization. The way we think about charge in everyday life is not wrong. It is incomplete in a very specific way. It is a low-energy approximation of something far richer and stranger. A surface-level description that works precisely because we are so far removed from the edges of physical possibility. When you feel a static shock, you're not glimpsing the true nature of charge. You're brushing against a tiny imbalance, quickly corrected, safely contained. When you watch a lightning strike, you are seeing a dramatic release of stored energy, but still one that obeys rules designed to keep the universe stable. These events are not precursors to the extremes. They are reminders of how far away those extremes really are. And yet the same underlying concept connects them all. The gentle flow in a wire, the crackle of static, the arc of lightning, the unimaginable densities near fundamental limits. They are different expressions of the same basic interaction, filtered through scale and circumstance. Understanding this helps us approach the deeper question with the right mindset. When we ask what happens as charge approaches the Planck limit, we're not asking what happens when electricity gets really strong in the everyday sense. We're asking what happens when the very assumptions that allow us to talk about electricity in the usual way begin to fail. The everyday whisper of charge becomes something else entirely. Not louder, but different in kind. And before we follow that transformation further, it's worth letting the familiar version of charge settle in the background, like a trusted companion whose limitations we're just beginning to notice. The way we think about electricity now is shaped by balance, stability, and scale. Those qualities have served us well. They have given us light, communication, comfort, and control. At some point in life, almost everyone has had the small surprise of a static shock. You reach for a metal handle, touch a light switch, or brush against another person, and there's that brief sting. It's over almost as soon as it begins, leaving behind a faint awareness that something invisible just happened. That moment, trivial as it seems, is one of the simplest ways charge announces itself. Not with drama, not with force, but with a quick reminder that electrical imbalance has been quietly building in the background. Static electricity is often where our story of charge buildup begins, because it feels personal and immediate. You don't need a power plant or a thunderstorm. All it takes is movement, friction, and the right conditions. Walking across a carpet in dry air is enough. As your shoes scrape along the surface, electrons are transferred from one material to another. Some materials are better at holding onto electrons, others are more willing to give them up. This difference is subtle, but over many tiny interactions it adds up. Each step you take can shift a few electrons. One step means nothing. 100 steps still mean almost nothing. But thousands of steps, especially when the air is dry and insulating, allow charge to accumulate. Your body becomes slightly negatively charged, carrying an excess of electrons. The carpet becomes slightly positive, missing the ones that wandered off. Nothing dramatic happens right away, because the imbalance is still small, and because air, under most conditions, acts as an insulator. The shock comes when the imbalance finally finds a path to equalize. Metal is an excellent conductor. When your finger approaches a doorknob, the electric field between you grows strong enough to tear electrons through the air gap. The air briefly ionizes, allowing charge to rush across in a tiny spark. The sensation is sharp because the discharge happens quickly. releasing stored energy in a very short time. This is charge buildup in its simplest form: friction, separation, accumulation, release. The same basic process scales up step by step into far larger and more impressive phenomena. Consider a balloon rubbed against hair. The balloon gains electrons, the hair loses them. Suddenly the balloon sticks to walls, attracts small bits of paper, and behaves as though it has a will of its own. Nothing new has been introduced. No new force has appeared. The same electromagnetic interaction is at work, only now it is visible in gentle motion rather than a brief sting. At this stage, charge buildup still feels manageable. The amounts involved are tiny. The forces, while noticeable, are weak. The system corrects itself easily once contact is made or moisture in the air allows charges to leak away. Nature restores balance without effort. As we move outward from these small-scale examples, the mechanisms remain the same, but the environment changes, materials differ, distances increase, insulation improves, and with those changes, charge can build to much larger levels before it is released. One of the most effective environments for charge buildup is the atmosphere itself. Air, under normal conditions, is a good insulator. Dry air, in particular, resists the flow of charge. This resistance allows electric fields to grow without immediately discharging. Add large volumes, constant motion, and phase changes between water, ice, and vapor, and you have the ingredients for something much bigger than a static shock. Inside a thundercloud, charge separation happens on a colossal scale. Warm air rises, carrying water droplets upward. As these droplets ascend, they cool and freeze, colliding with ice crystals and graupel, soft hail-like pellets. These collisions are not gentle. They involve impacts, fragmentation, and friction. And just like your shoes on a carpet, these interactions transfer electrons. Through a combination of temperature differences, collision dynamics, and material properties, electrons tend to be knocked loose from one type of particle and stick to another. Typically, lighter ice crystals acquire positive charge and are carried higher by updrafts, while heavier graupel becomes negatively charged and sinks toward the lower parts of the cloud. The result is a massive separation of charge over kilometers of vertical distance. Now the scale begins to matter. A thundercloud can hold billions of coulombs of separated charge. The electric field between the top and bottom of the cloud grows steadily stronger as more charge accumulates. Yet for a surprisingly long time, nothing happens. The air resists breakdown. It holds. The field strengthens further. This waiting period is crucial. It demonstrates that charge buildup is not simply about how much charge exists, but about where it exists and how well it is isolated. As long as the insulating properties of the air remain intact, the field can grow. The system stores energy quietly, invisibly, patiently. Eventually, though, the electric field becomes too strong. The air molecules begin to feel the strain. Electrons are torn from atoms. Ions form. Tiny conductive paths called streamers start to develop, branching through the air in search of a connection. When one of these paths finally bridges the gap between regions of opposite charge, the stored energy is released in a lightning strike. The lightning itself is not the build-up. It is the release. The build-up happens slowly, over many minutes, driven by countless collisions and separations. The discharge happens in a fraction of a second, bright, loud, and impossible to ignore. This contrast between slow accumulation and rapid release appears again and again in systems involving charge. It's not unique to thunderstorms. It shows up in capacitors, plasma discharges, and even in some astrophysical environments. Charge builds where it is allowed to remain separated. It releases where a path becomes available. What's important here is that even a thundercloud, immense as it is, represents only a modest extreme. The electric fields involved are strong by everyday standards, but still gentle compared to what physics allows in principle. The atmosphere breaks down long before reaching deeper limits. Air, for all its insulating ability, has a threshold. Beyond that threshold, it refuses to remain neutral. This pattern hints at something fundamental. Nature seems to provide escape routes long before truly extreme conditions are reached. Insulators fail, materials ionize, new pathways open, energy redistributes itself. As we move further away from Earth and into more exotic environments, charge buildup continues to follow the same basic logic, but the constraints change. In space, there is no air to break down, no moisture to leak charge away. Vast regions of near-perfect vacuum allow electric fields to persist over enormous distances. On the surfaces of airless bodies like the Moon or asteroids, charge can accumulate through interaction with sunlight and solar wind. Ultraviolet radiation knocks electrons loose from surface materials, leaving behind positive charge. Streams of charged particles from the Sun deposit additional charge. Without an atmosphere to neutralize these effects, electric fields can grow strong enough to lift dust from the surface, creating levitating layers of charged particles. In these environments, charge buildup is quieter than a thunderstorm, but no less real. It unfolds slowly, subtly, shaped by radiation and particle flows rather than friction and weather. Once again, separation is the key. As long as charges can remain apart, fields can grow. Astrophysical plasmas take this process even further. In the magnetospheres of planets, around pulsars, and within accretion disks surrounding compact objects, charge separation and buildup occur under extreme conditions. Magnetic fields twist, particles accelerate, and electric fields form in response to changing configurations. In some cases, these fields become strong enough to accelerate particles to nearly the speed of light. Even there, though, limits appear. Plasmas are remarkably good at neutralizing charge imbalances. If a region becomes too charged, particles rush in to compensate. Instabilities develop. Waves propagate. The system reorganizes itself. Extreme charge densities are fleeting, constantly undermined by the collective behavior of particles responding to fields. What all of these examples share is a tension between buildup and release. Charge accumulates when separation is maintained. It dissipates when pathways open, or when the environment can no longer support the imbalance. The larger the system, the more energy can be stored, but also the more mechanisms exist to undo that storage. This brings us back to how we intuitively think about charge. We often imagine it as something that piles up like sand in a heap. Add more grains and the pile grows taller. But charge doesn't behave like sand. It behaves more like tension in a stretched fabric. You can pull and pull, storing energy in the strain, but eventually the fabric responds. It tears, rearranges, or snaps back. As charge builds, it doesn't merely sit there. It actively reshapes its surroundings. Electric fields grow stronger. Forces increase. Energy density rises. At some point, the environment itself changes in response. At everyday scales, that response is simple. A spark jumps, air ionizes, a shock occurs. At atmospheric scales, lightning forms. In plasmas, instabilities erupt. At even more extreme scales, entirely new processes come into play, processes that challenge our ability to describe them using familiar concepts. And that is the quiet thread connecting static shocks to storm clouds and beyond. Charge builds through separation. It is held in place by insulation, distance, and structure. It grows until the system can no longer support it, and then it transforms, releasing energy in a way that restores balance. That restraint will matter more and more as we continue, because when we ask what happens as charge approaches the Planck limit, we're really asking how far this process can go before the universe changes the rules entirely. And that question only makes sense once we understand how charge builds in the first place, step by step, from the quietest shock to the most powerful storm, all following the same patient, persistent logic. When we first learn science, infinity tends to appear as a convenient idea rather than a serious one. Numbers can grow without bound, lines can extend forever, space can stretch endlessly in every direction. These notions feel clean and elegant, and in mathematics, they often work beautifully. You can let a variable increase indefinitely, and the symbols don't complain. They simply keep going. But the universe itself is not mathematics. It is physical. It has structure, texture, and consequences. And one of the quiet patterns that emerges again and again is that nature seems deeply uncomfortable with anything becoming truly infinite. This discomfort does not announce itself loudly. There is no universal rule etched into reality that says nothing may be infinite. Instead, limits appear indirectly. They emerge through breakdowns, instabilities, phase changes, and shifts in behavior. Push a system too far, and instead of growing without bound, it transforms. The rules change, new effects appear, old descriptions stop working. This pattern shows up everywhere once you begin to look for it. Take speed. For a long time, it seemed perfectly reasonable to imagine that objects could move faster and faster without limit, as long as you kept applying force. That intuition worked well for everyday experience. But when scientists began studying light and motion more carefully, they discovered a boundary. The speed of light is not just another large number. It is a limit. As an object approaches it, time slows, lengths contract, and energy requirements grow without bound. You never quite reach the limit. Instead, the universe reshapes the rules to prevent the idea of infinite speed from ever becoming physically meaningful. Temperature offers another example. At the cold end, we speak of absolute zero, a point where thermal motion reaches its minimum. You can get arbitrarily close, but you can never quite arrive. At the hot end, things become more subtle. Temperature is related to energy per degree of freedom, and as energy increases, new degrees of freedom appear. Molecules break apart, atoms ionize, particles are created. Rather than allowing temperature to climb smoothly toward infinity, nature keeps adding new ways for energy to distribute itself. Even density, which seems like it should be simple, resists becoming infinite. Classical equations allow you to compress matter arbitrarily, squeezing mass into smaller and smaller volumes. But when density rises, new forces intervene. Electrons resist being squeezed together. Neutrons push back. Quantum effects stiffen matter. Gravity grows stronger. Eventually, in our current understanding, matter collapses into black holes, objects where density becomes so extreme that our equations stop making sense. Infinity appears in the math, but physicists generally interpret that not as a real physical infinity, but as a sign that the theory has been pushed beyond its domain of validity. Charge follows the same pattern. At first glance, there seems to be no reason you couldn't keep adding charge to a system. Classical electromagnetism doesn't forbid it. The equations remain well behaved. Electric fields grow stronger, forces increase, energy density rises, but nothing explicitly breaks. On paper, charge can grow arbitrarily large. Yet the physical universe does not cooperate with this mathematical freedom. The moment charge begins to concentrate, it creates an electric field. That field stores energy. The more charge you add, the more energy accumulates in the surrounding space. Energy density increases not just linearly, but dramatically, as fields become more intense and confined. And energy, unlike abstract numbers, has consequences. It influences particles, it affects space-time, it destabilizes the vacuum. This is where nature's aversion to infinity becomes apparent. Rather than allowing charge density to grow without bound, the universe introduces new phenomena that divert, redistribute, or limit the buildup. One of the earliest interventions comes from quantum mechanics. At sufficiently strong electric fields, the vacuum itself becomes unstable. Virtual particles which normally flicker briefly into existence and vanish can be torn apart and made real. electron-positron pairs appear, siphoning energy out of the field. The stronger the field becomes, the more efficiently this process occurs. Instead of letting the field grow infinitely strong, the universe converts field energy into matter. This is not a coincidence, it is a recurring theme. Whenever a quantity threatens to diverge toward infinity, something new appears to absorb the excess. The system finds another way to store energy, another channel to dissipate stress. It is as though reality has built-in relief valves, each one activating only when necessary. Gravity provides another such valve. As the energy density of an electric field increases, its gravitational influence grows. Space responds, curvature intensifies, time behaves differently. At extreme levels, the energy stored in a field could, in principle, collapse into a black hole, not because of mass in the usual sense, but because energy itself gravitates. Once again, infinity is avoided. Instead of infinite charge density, you get a horizon, a boundary beyond which information cannot escape. The system does not become infinite, it becomes something else. This pattern extends beyond physics into more abstract realms. In thermodynamics, infinite efficiency is forbidden. In information theory, infinite information density is constrained. In computation, infinite speed or infinite memory runs into physical limits imposed by energy, noise, and causality. Every time infinity appears as a tempting endpoint, the universe gently steps in and redirects the path. Why does this happen? One way to think about it is that infinity is not a physical state, it is a signal. In equations, infinities usually indicate that a model has been pushed past the regime where its assumptions hold. The appearance of an infinity does not mean the quantity actually becomes infinite, it means the description has failed. This is why physicists treat infinities with suspicion. When calculations produce infinite answers, they don't celebrate, they worry. They look for missing physics. They search for a deeper theory that resolves the divergence into something finite and meaningful. Charge at the Planck scale fits squarely into this pattern. The Planck limit is constructed from fundamental constants: the speed of light, the gravitational constant, and Planck's constant. These numbers encode the deepest features of spacetime, energy, and quantum behavior. When charge densities approach this scale, our familiar theories overlap in ways they were never designed to handle. Electromagnetism, quantum mechanics, and gravity all demand to be taken seriously at the same time, and they disagree. Electromagnetism wants to let fields grow smoothly. Quantum mechanics introduces fluctuations and particle creation. Gravity insists that energy curves space. None of these effects can be ignored. None can dominate completely. The result is a regime where no single description works on its own. In this sense, the Planck limit is not a hard ceiling. It is a warning label. It tells us that the language we're using is about to stop being useful. Asking what happens beyond it using the same concepts is like asking what lies north of the North Pole. The question itself begins to lose meaning. This helps explain why the universe rarely says infinite. Infinity is not something you reach. It is something you encounter when you ask a question using the wrong framework. The physical world responds by changing the framework. Even black holes, often thought of as infinite density objects, likely do not contain true infinities. The singularities predicted by general relativity are almost certainly artifacts of pushing the theory beyond its valid range. Most physicists believe that a quantum theory of gravity would replace those singularities with something finite, though still extreme and unfamiliar. Charge, similarly, is expected to remain finite in any physically meaningful sense. The universe does not allow unlimited accumulation in a fixed form. It disperses, transforms, or hides excess through mechanisms that preserve overall consistency. There is also a deeper philosophical reason this pattern makes sense. Physical quantities are defined through measurement, and measurement always involves interaction. Interaction requires energy. Energy has limits. No measurement can access infinite values because no finite system can interact with something infinite without being overwhelmed or destroyed. In this view, infinity is not just physically unattainable, it is operationally meaningless. If you cannot, even in principle, interact with or measure an infinite quantity, then it does not belong to the domain of physics. It belongs to mathematics, where symbols can roam freely without consequence. Nature, by contrast, is conservative. It budgets energy carefully. It enforces causal structure. It balances forces and responds to stress. When pushed, it does not explode into infinities. It reorganizes. This reorganization often takes the form of new layers of description. Classical physics gives way to quantum physics. Quantum physics gives way to relativistic physics. Relativistic physics hints at quantum gravity. Each layer resolves infinities that appeared in the one before it, replacing them with new concepts that make extreme situations finite again. So when we talk about limits in nature, we are not talking about barriers in the sense of walls you crash into. We are talking about transitions, points where one way of describing reality hands off to another, points where asking the same question in the same way no longer works. Charge reaching the Planck limit is one of those points. It is not that charge suddenly becomes infinite or forbidden. It is that charge, as a standalone concept, dissolves into something more complex. It becomes inseparable from spacetime, from quantum fluctuations, from energy itself. The universe does not say no. It says different. This perspective also explains why these limits feel so far removed from everyday life. They are not boundaries we brush against casually. They are deep structural features of reality, only revealed when we push our theories to their extremes. Most of the time, we live comfortably within regimes where simple descriptions apply, where charge flows, fields behave, and balance is easily restored. But the quiet presence of limits shapes everything nonetheless. It is why stars shine steadily, instead of blowing themselves apart instantly. It is why atoms hold together. It is why the universe evolves rather than collapsing into chaos or freezing into perfection. Infinity, if it existed physically, would be destabilizing. An infinite field, an infinite density, an infinite force would dominate everything, leaving no room for structure or change. The absence of such infinities is not a flaw. It is the reason complexity is possible at all. As we continue, this idea will keep returning in different forms. Each time we approach an extreme, we will see how the universe avoids going all the way, how it redirects excess into new channels, how it preserves coherence by refusing to let any single quantity run away unchecked. When physicists talk about the Planck scale, they are not pointing to a place you could ever visit, or a size you could ever see, even with the most powerful microscope imaginable. They are pointing to a boundary in understanding, a region where our usual tools for describing reality start to lose their sharp edges. Measurements that once felt precise become fuzzy. Concepts that once felt solid begin to overlap, and questions that once had clear meaning start to quietly change shape. The Planck scale is built from a small set of numbers that appear everywhere in fundamental physics. The speed of light, which governs how fast information and influence can travel. Planck's constant, which sets the scale of quantum effects and tells us that nature is not infinitely divisible, and the gravitational constant, which measures how strongly energy and mass curve space and time. When you combine these constants in just the right way, you get natural units of length, time, energy, and charge that do not depend on human conventions. They are not chosen, they emerge. The Planck length, for example, is unimaginably small. It is so far removed from everyday scales that even calling it tiny feels inadequate. To put it into perspective, a proton is enormous compared to the Planck length, and a proton itself is already far beyond direct human intuition. The Planck time is equally alien, representing an interval so short that light barely has time to move at all. These scales do not describe small objects in the usual sense. They describe the smallest meaningful distinctions the universe seems willing to make. What matters is not the numbers themselves, but what happens when we try to push our descriptions toward them. At ordinary scales, measurement feels straightforward. You can measure length by laying down a ruler. You can measure time by counting oscillations in an atom. You can measure charge by observing forces or currents. There is always some uncertainty, of course, but it is usually small enough to ignore. With better instruments, better techniques, and enough patience, you can always do better. As you move toward the Planck scale, that confidence erodes. Quantum mechanics tells us that certain pairs of measurements cannot both be made arbitrarily precise. Position and momentum are the classic example. The more precisely you know one, the less precisely you can know the other. This is not a limitation of technology. It is a feature of reality. The act of measurement itself disturbs what is being measured. At larger scales, this disturbance is negligible. At smaller scales, it becomes significant. Near the Planck length, it becomes overwhelming. To probe such small distances, you would need enormous energy, because shorter wavelengths require higher energies. But concentrating that much energy into such a small region has consequences. According to general relativity, energy curves space. Push enough energy into a tiny volume, and instead of revealing finer structure, you create a gravitational collapse. In other words, the more you try to sharpen your measurement, the more you blur it. This is one of the clearest signs that the Planck scale is not just about smallness. It is about interference between the fundamental pillars of physics. Quantum mechanics demands energy to resolve small features. Gravity responds to that energy by reshaping space-time. The act of looking changes what there is to see. Charge behaves no differently in this regard. At everyday scales, charge is something you can measure cleanly. You can count electrons, you can measure currents, you can calculate fields and forces with remarkable accuracy. The electromagnetic interaction is the most precisely tested theory in physics, agreeing with experiments to astonishing precision. But that precision rests on assumptions. It assumes space-time is smooth. It assumes the vacuum behaves passively. It assumes that charge can be localized without fundamentally altering the structure of space around it. Those assumptions hold until they don't. As charge density increases, so does the energy density of the associated field. At moderate levels, this energy is just another entry in an equation. At extreme levels, it becomes an active participant. It fluctuates, it gravitates, it destabilizes the vacuum. Near the Planck scale, the distinction between charge and energy begins to blur. Charge is no longer just something that produces a field. The field itself carries energy, and that energy feeds back into the geometry of space. The clean separation between source and effect breaks down. Measurement becomes ambiguous because the object being measured cannot be isolated from the act of measurement or from its own influence on the surrounding space-time. Another way to think about this is that the Planck scale marks the point where our units stop being independent. In everyday physics, you can measure charge without worrying about gravity. You can measure length without worrying about quantum uncertainty. You can measure time without worrying about space-time curvature. At the Planck scale, everything talks to everything else. Charge influences energy. Energy influences gravity. Gravity influences time. Time influences measurement. There is no longer a hierarchy of effects. There is only a tightly coupled system. This coupling is what causes the blur. Imagine trying to draw a map of a landscape that changes shape every time you look at it. The more closely you examine a hill, the more the ground beneath your feet shifts. The act of observing reshapes the terrain. No matter how careful you are, the map refuses to settle into a fixed form. That is what the Planck scale does to measurement. This is also why physicists often describe this regime using the language of limits rather than predictions. We can estimate where our theories break down. We can calculate when certain effects become unavoidable. But we cannot yet say with confidence what actually replaces our familiar descriptions beyond that point. The Planck scale is not a wall you hit. It is a region where the very idea of hitting a wall stops making sense. This has important consequences for how we think about charge near this boundary. Asking how much charge is there assumes that charge can be cleanly defined, localized, and measured independently of everything else. Near the Planck scale, those assumptions fail. Charge becomes inseparable from the quantum structure of the vacuum and the geometry of spacetime. In practical terms, this means that pushing charge toward the Planck limit does not result in a neatly defined maximum value that you could write down and compare to something else. Instead, it results in a loss of clarity. The system no longer supports a description where charge is a standalone quantity. This is deeply counterintuitive because we are used to thinking of limits as numbers, a maximum speed, a minimum temperature, a highest voltage. But the Planck scale teaches a different lesson. Some limits are not numerical, they are conceptual. They tell you not, you may not go further, but you may not ask the same question anymore. This idea appears repeatedly in attempts to unify physics. In quantum gravity research, one of the recurring themes is that space-time itself may not be fundamental. It may emerge from more basic relationships. If that is true, then concepts like distance and duration are not primary at the deepest level. They are approximations that work when the underlying structure behaves smoothly. If space and time are emergent, then fields that live in space and evolve in time, including electromagnetic fields, are also emergent. Charge, as a property of particles interacting with those fields, becomes a derived concept rather than a fundamental one. Near the Planck scale, we may be probing the regime where emergence itself begins, where the smooth picture dissolves into something more discrete, more relational, or more abstract. This is why measurements blur. There is no sharp boundary to detect because the thing you are trying to measure does not exist in the same way anymore. It is tempting to imagine that with better technology, we could eventually overcome this blur, build smaller probes, generate higher energies, improve precision indefinitely. But the Planck scale is not a technological barrier, it is a physical one. It arises from the interplay of the deepest constants in nature. No amount of clever engineering can bypass the fact that energy curves space, or that quantum uncertainty is fundamental. In this sense, the Planck scale represents a kind of humility built into the universe. It reminds us that there are limits to how finely reality can be resolved. Not because we are inadequate observers, but because the act of observation is part of reality itself. For charge, this humility manifests as a refusal to let extreme concentrations remain well defined. As charge density increases, new phenomena appear that smear out localization, redistribute energy, and entangle the system with its surroundings. Measurement outcomes depend on context. Values fluctuate. Definitions overlap. This does not mean that physics fails. It means that physics transitions. Just as classical mechanics gives way to quantum mechanics at small scales, and Newtonian gravity gives way to general relativity at high energies, our familiar picture of charge gives way to something more subtle near the Planck scale, something we are still trying to articulate. And that uncertainty is not a flaw, it is an invitation. It invites new theories, new frameworks, new ways of thinking that do not rely on sharp separations between objects, fields, and space. It suggests that at the deepest level, reality may be less like a collection of things and more like a network of relationships. There comes a point, as charge continues to build, when the familiar language we use to describe it starts to feel strained. Up to now, we've been able to talk about charge gathering separating and releasing itself in ways that still resemble everyday experience, just scaled up. Static shocks become lightning. Lightning becomes planetary electric fields. Planetary fields blend into astrophysical plasmas. Each step feels larger, but not fundamentally different. The rules seem to hold. Repulsion increases, fields grow stronger, energy accumulates. Nothing appears to object too loudly. But crowding is different from mere accumulation. When charge crowds itself, it is no longer simply present in large amounts. It is confined, forced into proximity with itself despite its own resistance, and that resistance is not subtle, like charges repel each other with a force that does not weaken easily. Every additional unit of charge added to an already charged region must fight against all the charge that came before it. The energy cost rises quickly, and not in a gentle linear way. At modest densities, this is manageable. You can keep piling charge into a capacitor by increasing the voltage. The electric field inside grows stronger, the energy stored rises, the system remains stable, because the materials involved, the geometry and the surrounding environment are designed to tolerate the stress. But even here, there are limits. Dielectrics break down, insulators fail, sparks form. The system finds a way to discharge itself. Those failures are not accidents, they are warnings. They tell us that charge does not like being crowded. It tolerates proximity only when the environment provides enough structure to keep it apart or enough freedom to let it escape. Remove those safety valves, and the situation changes rapidly. Now imagine continuing past those everyday failures. Imagine materials that do not break down. No air to ionize, no structure to collapse. Just charge confined by sheer force and energy. At this point, the only thing holding the system together is the very interaction that wants to tear it apart. The electric field becomes immense, not just strong in a human sense, but strong in a way that challenges the vacuum itself. The space around the charge is no longer passive. It is saturated with energy. Every point in that region carries tension, like a stretched membrane pulled tighter and tighter. This is where crowding becomes the dominant feature of the system. When charge crowds itself at extreme densities, the energy stored in the field grows so large that it begins to rival other fundamental scales. Quantum fluctuations, usually small and fleeting, start to matter. The vacuum is no longer quiet. Virtual particles appear more frequently, linger longer, and interact more strongly with the field. At a certain point, the field does not merely influence particles, it creates them. Electron-positron pairs can be pulled out of the vacuum itself. This is not a metaphor. The energy stored in the electric field becomes sufficient to turn empty space into matter. These newly created charges immediately respond to the field, partially screening it, reducing its strength, and redistributing energy. This process is nature's first serious intervention. Instead of allowing charge to crowd indefinitely, the universe opens a new channel. Excess energy becomes particles. Those particles carry charge. They move. They rearrange the field. The crowd begins to thin, not because charge disappears, but because it spreads into new degrees of freedom. The stronger the field becomes, the more efficient this process grows. The vacuum, once thought of as empty, reveals itself as a reservoir of possibilities, ready to step in when fields grow too intense. In this way, crowding triggers its own relief. But suppose we keep going. Suppose we imagine a scenario where even particle creation is not enough to fully relieve the pressure. Perhaps the geometry confines everything. Perhaps symmetry demands that charge remain concentrated. Perhaps we are pushing not a real physical system, but the limits of theory itself. Now the energy density becomes truly extreme. At these levels, gravity can no longer be ignored. Energy is mass. Mass curves space-time. When the energy stored in an electric field becomes large enough, it begins to significantly distort the geometry around it. Space does not merely host the field, it responds to it. Time slows, distances warp. Paths that once seemed straight bend inward. The field's own energy contributes to a gravitational pull that acts back on the system. This feedback loop is critical. Charge creates a field. The field stores energy. The energy curves space-time. Curved space-time alters how the field behaves. The system becomes self-referential, with no clear separation between cause and effect. Crowding is no longer just an electromagnetic issue, it becomes a gravitational one. At this stage, adding more charge does not simply increase repulsion, it deepens curvature. it intensifies confinement. Paradoxically, gravity, which is normally negligible in discussions of charge, begins to assist in keeping charge together, not because it prefers charge, but because it responds indiscriminately to energy. This tension between repulsion and confinement pushes the system toward a critical boundary. That boundary is not marked by a single event. There is no flash, no sudden transition where a sign flips from allowed to forbidden. Instead, descriptions start to overlap. Electromagnetism alone is no longer sufficient. Quantum field theory alone is no longer sufficient. General relativity alone is no longer sufficient. All three must be considered simultaneously, and that is precisely where our current understanding falters. As charge crowds itself further, the characteristic length scales of the system shrink. The region containing the charge becomes smaller. The field gradients become steeper. Energy density rises faster than volume decreases. Eventually, the scale of variation approaches the Planck length. This is the ultimate boundary we've been circling. At the Planck scale, the very idea of locality becomes uncertain. You can no longer say with confidence where the charge is or how sharply it is confined. Quantum uncertainty ensures that attempts to localize it introduce fluctuations large enough to destabilize the region. Gravitational effects ensure that those fluctuations feed back into spacetime itself. Crowding at this point ceases to mean what it used to mean. Instead of charges pressing against one another in space, we are dealing with a situation where space itself is under stress. The field energy is no longer a thing sitting inside space. It is part of what space is doing. The distinction dissolves. Some theoretical models suggest that under these conditions, space-time may undergo a kind of phase change. Rather than remaining smooth and continuous, it may become discrete, foamy, or fragmented. Distances fluctuate. Causal structure becomes uncertain. The background on which charge once lived becomes an active participant in the drama. In such a regime, asking how much charge is present becomes ambiguous. Charge is defined through interactions, but interactions require a stable space-time framework. If that framework is fluctuating, the definition itself wobbles. This is why the idea of an ultimate boundary is so important. It is not a maximum in the ordinary sense. It is a point beyond which the question loses precision. You can no longer crowd charge in the way you once imagined, because the stage on which that crowding occurs has changed. Nature does not allow charge to become arbitrarily dense while everything else stays the same. Instead, everything else changes. This pattern echoes what we saw with infinities more broadly. When a quantity threatens to diverge, the system does not permit the divergence. It redirects, it transforms, it replaces one description with another. In the case of extreme charge crowding, the redirection appears to involve the emergence of new physics. Perhaps quantum gravity smooths out what would otherwise be singular. Perhaps charge becomes delocalized across networks of relationships rather than concentrated at points. Perhaps spacetime itself enforces a kind of minimum volume for energy density. We do not yet know the details. What we do know is that every serious attempt to push charge toward this boundary encounters resistance not from a single force, but from the structure of reality itself. This resistance is not violent, it is subtle. It manifests as instability, ambiguity, and loss of definition rather than explosive rejection. The equations grow sensitive. Small changes produce large effects. Predictions depend strongly on assumptions. This sensitivity is itself a signal that we are approaching a limit. It is tempting to imagine that somewhere beyond this boundary lies a final answer, a precise maximum charge, a clean cutoff, a number written in natural units that says, this is as far as it goes. But nature rarely offers such simplicity. Instead, it offers a transition zone. In that zone, charge is no longer a standalone actor. It becomes inseparable from energy, from space-time, from quantum structure. Crowding no longer means piling more of the same thing into a smaller space. It means reshaping the system until the original concept dissolves. This has an important implication. When we ask what really happens as charge approaches the Planck limit, we should not expect a dramatic finale. There is no cosmic explosion marking the moment charge reaches its maximum. There is no universal alarm bell. What happens instead is quieter and stranger. The system loses the ability to support extreme crowding without changing its identity. Charge stops behaving like charge. Space stops behaving like space. Time stops behaving like time. The familiar pieces of our description blur together into something we do not yet have the language to fully describe. And that is not a failure of imagination. It is a reflection of how deeply our everyday concepts are tied to scales far removed from these extremes. When charge reaches the point where it can no longer quietly exist within its surroundings, the first thing to notice is that the surroundings stop behaving like a passive container. Up to now, we have treated space as a stage, a backdrop against which charge accumulates, separates, and crowds itself. Fields stretch across it. Particles move through it. Measurements take place within it. Space, in this familiar picture, remains unchanged no matter how intense the action becomes. That assumption works astonishingly well for most of physics. It holds through static shocks, thunderstorms, electrical machines, plasmas, and even much of high-energy particle physics. Space appears stable, neutral, and indifferent. You can pour enormous amounts of electromagnetic energy into a region, and space-time barely flinches. But that indifference is not infinite. As charge becomes extreme, as fields intensify and energy density climbs, space itself begins to respond. Not metaphorically, not symbolically, physically. The strain placed on the electromagnetic field does not remain confined to the field. It propagates outward, pressing on the very geometry of the universe. To understand why, it helps to remember that fields are not abstract bookkeeping devices. An electric field is not just a set of arrows drawn on paper, it is a physical entity with energy and momentum. Wherever there is an electric field, there is energy stored in space, and wherever there is energy, gravity listens. This connection is easy to forget because gravity is usually so weak compared to electromagnetism. Between two electrons, the electric repulsion is vastly stronger than their gravitational attraction. In everyday circumstances, gravity is utterly irrelevant when discussing charge. You can safely ignore it, and physics rewards you with accurate predictions. But strength is not the only thing that matters. Concentration matters. As fields grow stronger and more tightly confined, the energy density associated with them increases dramatically. Energy per unit volume rises. At first, this is just another number in an equation, but as that number grows, it begins to influence space-time curvature in a measurable way. General relativity tells us that space-time is not a rigid grid. It is flexible. It curves in response to energy and momentum. Mass is just one form of energy. Radiation counts too. Pressure counts. Stress counts. The energy stored in an electric field counts. When an electric field becomes extreme, the stress energy it carries becomes comparable to other sources that significantly curve space-time. Space no longer remains flat and unaffected. It begins to bend, stretch, and compress in response. This bending is not something you could see directly. There is no visual ripple or glow marking the moment space begins to react. Instead, the effects appear indirectly. The paths of particles change. The propagation of fields shifts. Time itself begins to behave differently within the strained region. One way to picture this is to imagine space as an elastic medium, not in a literal sense, but as an analogy. At low strain, you can press on it without noticing much response. It feels firm and stable, but as the pressure increases, subtle deformations appear. Lines that once seemed straight curve slightly. Distances that once added cleanly begin to behave oddly. At extreme strain, the material no longer behaves as it did before. New modes of deformation appear, old assumptions fail. In the context of extreme charge, this strain arises because the electric field does not merely exist in space. It fills space. It occupies it. When the field becomes intense enough, the energy density associated with it effectively weighs down the region. Spacetime responds by curving inward, altering the geometry in which the field itself exists. This creates a feedback loop. The charge generates a strong electric field. The field stores energy. The energy curves space-time. Curved space-time modifies how the field propagates and how charge interacts. That modification can further concentrate energy, deepening the curvature. At everyday scales, this loop is completely negligible. At extreme scales, it becomes central. What makes this especially interesting is that the curvature does not simply oppose the electric repulsion. Gravity does not cancel electromagnetism. Instead, it reshapes the environment in which electromagnetic interactions take place. It changes distances, time intervals, and the way fields spread out. As space curves inward, the region available for the field to occupy changes. Field lines that would normally spread out are forced closer together. This can increase local field strength even further, intensifying the strain. At the same time dilation slows down processes within the region relative to the outside world. This slowing of time is not just a clock effect. It affects dynamics. It alters rates of interaction. It changes how instabilities develop and how energy redistributes itself. From the outside, the system begins to look frozen, locked into a state of extreme tension. From the inside, the experience is different. Processes continue, but under conditions where familiar scales no longer apply. This is one reason extreme charge configurations are so difficult to describe. There is no single perspective that captures everything cleanly. Observers inside and outside the strained region disagree about timing, distances, and energy flows. The concept of a single, global description begins to fracture. Another crucial aspect of fields under strain is that they do not remain smooth. At high energies, quantum fluctuations become significant. The vacuum itself becomes restless. Instead of a uniform background, space begins to seethe with transient structures. Tiny fluctuations in the field grow, interact, and sometimes dominate local behavior. These fluctuations are normally averaged out. In weak fields, they cancel each other, leaving behind smooth, predictable behavior. In extreme fields, the balance tips. Fluctuations can become amplified rather than suppressed. This amplification is not random. It follows patterns dictated by the underlying interactions. Certain modes grow faster. Certain configurations become unstable. The field can fragment into domains, oscillate violently, or trigger cascades of particle creation. From the outside, this looks like chaos. From the inside, it is the system exploring every available way to relieve strain. One of the most striking consequences of this regime is that space itself can no longer be treated as continuous in the usual sense. Many approaches to quantum gravity suggest that at scales near the Planck length, space-time develops a granular or discrete structure. Distances fluctuate. Geometry becomes probabilistic rather than fixed. Under extreme charge-induced strain, this granularity may become relevant. The field no longer spreads smoothly across a continuum. Instead, it interacts with a space-time structure that has its own dynamics, its own limits, and its own response to stress. This makes the notion of a field living in space somewhat misleading. At these scales, the field and space are intertwined. You cannot fully describe one without describing the other. This intertwining has deep consequences for how charge behaves. Charge is defined by how it couples to a field. The field is defined by how it propagates through space. If space itself is fluctuating, then the definition of charge becomes context-dependent. In other words, extreme charge does not just strain space, it strains meaning. Concepts that once felt crisp become relational. Instead of asking, how strong is the field here? You must ask, strong relative to which geometry, which observer, which scale? The answers differ, not because of confusion, but because the system no longer supports a single universal description. This may sound abstract, but it reflects a very concrete lesson from modern physics. Whenever energy densities become extreme, the background ceases to be background. It becomes part of the system. We see this lesson in black holes, where space-time curvature dominates behavior. We see it in the early universe, where energy density shaped expansion itself, and we see it here, where extreme charge forces space to participate actively. Importantly, this participation is not optional. Space cannot choose to remain flat while accommodating arbitrarily intense fields. The equations of general relativity enforce a response. Curvature is not an afterthought. It is inevitable. This inevitability is another reason why nature avoids infinities. Infinite field strength would imply infinite energy density. Infinite energy density would imply infinite curvature. Infinite curvature would imply a breakdown of space-time itself. Instead of allowing that cascade, the universe intervenes earlier through instability, particle creation, and geometric response. The strain distributes itself across multiple layers of reality. Electromagnetism tries to push charge apart. Quantum mechanics introduces fluctuations and new particles. Gravity curves space and slows time. Each layer absorbs part of the stress. None allows the system to remain simple. This layered response is what makes extreme charge so fascinating. It is not just an electromagnetic problem. It is a full system problem involving every fundamental interaction. As fields strain space, horizons can form. Boundaries emerge beyond which information cannot easily escape. These horizons are not necessarily black hole horizons in the traditional sense, but they play a similar role. They limit communication. They separate regions of space-time with different properties. Once horizons appear, the system acquires an internal structure that cannot be described from a single viewpoint. Observers inside and outside experience different realities. The notion of a unified field configuration dissolves into patches, each governed by its own effective rules. At this point, the idea of continuing to add charge becomes meaningless. You cannot simply pile more onto a system that no longer has a single coherent space to contain it. The act of adding becomes inseparable from restructuring. This brings us back to the central theme that has been quietly developing. The universe does not forbid extremes by issuing decrees. It forbids them by changing the context in which they would occur. When fields are placed under extreme strain, space responds not by breaking, but by participating. It bends, fluctuates, fragments, and reorganizes. In doing so, it prevents the conditions required for infinite charge density from ever being realized in a stable, well-defined way. And this response is not something that happens at a single, dramatic moment. It unfolds gradually as energy density increases. Small curvatures become noticeable, fluctuations grow louder, feedback loops tighten, descriptions blur. By the time we approach the ultimate boundary, space is no longer a silent witness. It has become an actor, shaping and reshaping the behavior of fields in ways that cannot be ignored. Long before anything dramatic happens, long before equations collapse or concepts fall apart, there are quiet signals that a system is under stress. Physics is generous in that way. It rarely allows a breakdown to arrive without warning. Instead, it scatters subtle clues throughout the behavior of a system, small deviations from the expected, gentle irregularities that hint something deeper is changing. When charge is pushed toward extreme concentrations, these clues appear first not in charge itself, but in energy density. Energy density is an unassuming idea. It simply means how much energy exists in a given volume of space. In everyday life, we rarely think about it. A warm cup of tea has more energy than a cold one. A stretched spring stores energy. A moving car carries kinetic energy. None of these situations feel particularly exotic because the energy is spread out, diluted across space and time. Electric fields store energy too. Every region of space threaded by an electric field contains energy proportional to the square of the field strength. At low field strengths, that energy is negligible. At moderate strengths, it becomes useful. At high strengths, it becomes important. And at extreme strengths, it becomes decisive. What matters is not just how much total energy exists, but how tightly it is packed. You can have a tremendous amount of energy spread across a large region with very little consequence. A star emits enormous energy every second, yet space around it remains relatively well behaved. But compress that same amount of energy into a much smaller volume, and everything changes. Forces intensify, fields steepen, space responds. As charge crowds itself, the associated electric field grows stronger and more localized. Energy density increases rapidly. At first, this increase produces no surprises. Calculations still work. Predictions still align. The system behaves like an exaggerated version of familiar physics. Then the first warning signs appear. One of the earliest signs is nonlinearity. In simple systems, doubling a cause doubles the effect. Double the charge, and the field doubles. Double the field, and the force doubles. But as energy density climbs, this proportionality starts to fail. Small increases in charge produce disproportionately large changes in behavior. Fields begin to interact with themselves indirectly through the medium of space and the vacuum. This loss of linearity is subtle. It does not announce itself with explosions or singularities. Instead, calculations become sensitive. Tiny changes in initial conditions lead to noticeably different outcomes. Approximations that once worked beautifully begin to drift. This sensitivity is not numerical sloppiness. It is physical. It reflects the fact that the system is no longer governed by a single dominant interaction. Multiple layers of physics are becoming entangled. Another warning sign appears in the behavior of fluctuations. At low energy densities, fluctuations are background noise. Quantum fields jitter constantly, but their effects average out. You can ignore them without penalty. At higher densities, those fluctuations begin to matter. The background noise grows louder. Certain modes become amplified rather than suppressed. In strong electric fields, virtual particle pairs appear more frequently. Normally they annihilate almost instantly. But as energy density increases, the field can pull them apart faster than they can recombine. What was once a transient fluctuation becomes a real, observable particle. This transition is gradual. There is no sharp threshold where the vacuum suddenly becomes unstable. Instead, the rate of particle creation increases smoothly as the field strengthens. Each created particle carries away a bit of energy and charge, slightly reducing the field that created it. This behavior is a warning sign, not a solution. It tells us that the system has entered a regime where the vacuum is actively participating. Empty space is no longer empty. It has become a dynamic component of the system responding to stress by changing its state. At the same time, the presence of these particles feeds back into the field. Newly created charges alter the electric field configuration. They screen it, distort it, and introduce new interactions. The field becomes less uniform, more textured, more complex. This complexity is another signal. As energy density rises, systems tend to develop structure. Smooth configurations become unstable. Domains form. Oscillations appear. Instead of a single, clean field profile, you get a shifting landscape of peaks and valleys. The system explores alternative configurations in search of stability. This is not unique to electromagnetism. It happens in fluids, solids, plasmas, and even biological systems under stress. When pushed too hard, simple order gives way to richer, more complicated patterns. In the context of extreme charge, these patterns reflect the system's attempt to redistribute energy. Crowding energy into one region becomes increasingly costly. The system responds by spreading it out in new ways, even if that means creating entirely new entities to carry it. Another warning sign lies in time itself. As energy density increases and space-time curvature becomes relevant, time dilation effects grow. Processes within the strained region slow relative to the outside world. This is not just a curiosity. It changes how energy flows, how instabilities develop, and how feedback loops operate. From an external perspective, the system seems to approach a frozen state. Changes happen more and more slowly. From the inside, however, dynamics continue, but under conditions where timescales are stretched and distorted. This mismatch in temporal behavior is a clue that the system is approaching a boundary where a single, global description breaks down. When different observers cannot agree on rates, durations, or sequences of events, the notion of a unified evolution becomes fragile. Energy density also leaves its mark on geometry. At modest levels, the curvature induced by field energy is tiny. You can safely ignore it. As density rises, curvature becomes noticeable. Distances measured within the field differ from distances measured far away. Paths that would normally be straight begin to bend. This geometric response is another early warning. It tells us that the system is no longer confined to electromagnetism. Gravity has joined the conversation. Once gravity participates, everything changes, because gravity does not saturate. It always responds to energy, no matter its form. The involvement of gravity introduces a new kind of instability. Regions of high energy density can become self-trapping. Instead of dispersing, energy can become confined by the very curvature it creates. This confinement increases density further, strengthening curvature even more. This positive feedback is dangerous. In many systems, positive feedback signals an impending transition. It means the current configuration cannot remain stable indefinitely. Either the system will reorganize into a new phase, or our description will cease to apply. At this stage, the warning signs accumulate. Calculations become delicate. Small perturbations matter. Fluctuations grow. Geometry responds. Time behaves oddly. None of these effects alone signals catastrophe. Together, they form a pattern. That pattern tells us we are nearing a breakdown of the familiar framework. It is important to emphasize that breakdown does not mean destruction. It does not mean the universe fails. It means our chosen description stops being adequate. The system itself continues, but it does so under rules we have not yet fully articulated. Energy density is central to this transition, because it is the quantity that ties everything together. Charge creates fields. Fields store energy. Energy influences quantum behavior. Energy curves space-time. Energy determines stability. As long as energy density remains below certain thresholds, these effects can be separated. Above those thresholds, separation becomes impossible. Another subtle sign appears in the way conservation laws are applied. At low energies, conservation of charge, energy, and momentum feel absolute and straightforward. At high energy densities, especially in curved space-time, these laws become more subtle. Energy can be localized only approximately. Defining total energy in a dynamic space-time becomes tricky. Charge conservation still holds, but the way charge is distributed and measured becomes observer-dependent. This does not mean conservation laws fail. It means they require more careful interpretation. The familiar bookkeeping methods no longer suffice. That need for reinterpretation is itself a warning sign. Whenever a physical quantity requires increasingly elaborate definitions to remain meaningful, it suggests that the underlying concept is being stretched beyond its natural domain. Energy density near extreme charge configurations pushes us exactly into that situation. We can still write down equations. We can still track quantities, but each step requires more context, more qualifiers, more assumptions. The simplicity that characterized earlier stages is gone. Another sign lies in the role of scale. At moderate energies, you can zoom in or out without fundamentally changing the description. The same laws apply. At extreme energy densities, scale matters intensely. Behavior at one scale does not smoothly extrapolate to another. Small-scale fluctuations can dominate large-scale behavior. Averaging no longer works cleanly. This sensitivity to scale is a hallmark of critical phenomena. Systems near phase transitions display exactly this kind of behavior. Small disturbances have outsized effects. Correlations grow long-ranged. The system teeters between competing configurations. It is increasingly clear that pushing charge toward the Planck limit places the system in a critical regime. Not critical in the sense of imminent disaster, but critical in the technical sense of being poised between phases. On one side lies the familiar world of fields in smooth spacetime. On the other lies an unknown regime where spacetime itself may be emergent, discrete, or relational. Energy density is the control parameter guiding this transition. As it increases, the system explores new possibilities. Particle creation, curvature, time dilation, and fluctuation amplification are not random side effects. They are structured responses to stress. They are the universe's way of signaling that something fundamental is about to change. Importantly, none of these warning signs appear suddenly at the Planck scale. They begin much earlier, creeping in gradually as energy density rises. This gradual onset is what allows physicists to study them, to recognize patterns, and to infer the existence of deeper limits, even without directly reaching them. It is also what allows nature to remain stable. By introducing new effects early, the universe avoids abrupt, uncontrolled behavior. Stress is redistributed across multiple layers, preventing any single quantity from running away unchecked. In this sense, the warning signs are protective. They slow the system down. They complicate it. They force energy into new forms. Each intervention reduces the likelihood of a catastrophic divergence. From a human perspective, this can feel frustrating. We like clean limits. We like precise answers. We would prefer a single number that says how much charge is too much. But the universe does not operate that way. It prefers processes over thresholds, transitions over barriers. Energy density is the language it uses to communicate this preference. By watching how systems behave as energy density rises, we learn where our descriptions begin to fail. We learn which assumptions are fragile and which are robust. We learn that extreme charge is not just a question of electromagnetism, but a full system problem involving quantum behavior, space-time geometry, and the nature of measurement itself. For most of our journey so far, particles have behaved themselves. They have followed rules we can summarize, approximate, and rely on. Electrons repel each other. Fields respond smoothly. Fluctuations stay small enough to ignore. Even when things became intense, there was still a sense of order, a feeling that the system, while strained, remained legible. That sense begins to fade when quantum effects stop whispering and start making themselves impossible to overlook. Quantum mechanics is always present. Even in the calmest, most ordinary situations, particles are never perfectly still, never perfectly localized, never perfectly predictable. They jitter, they fluctuate, they explore possibilities. But under normal conditions, those behaviors average out. The randomness remains hidden beneath stable patterns, and classical intuition remains mostly intact. Extreme energy density changes that balance. As charge crowds itself and fields intensify, the quantum nature of particles can no longer be treated as a small correction, layered on top of an otherwise orderly picture. Instead, it becomes central. The fluctuations grow larger, the probabilities sharpen. The idea that particles have well-defined properties at all times becomes increasingly difficult to sustain. This is where the polite behavior ends. One of the first changes appears in localization. At low energies, you can talk about where a particle is with reasonable confidence. Not perfect certainty, but enough that the concept of position feels meaningful. As energy density increases and confinement tightens, attempts to localize particles more precisely inject more energy into the system. That energy feeds quantum fluctuations. Instead of pinning a particle down, you make it more restless. The particle's wave-like nature becomes pronounced, its position spreads out, its momentum becomes uncertain. The more you try to force it into a small region, the more violently it resists, not through conscious effort, but through the structure of quantum law. At extreme charge densities, this resistance becomes impossible to ignore. Particles refuse to remain neatly separated. Their wave functions overlap. Distinctions blur. The idea of counting individual particles becomes ambiguous because their identities begin to intertwine. This is not just a mathematical inconvenience. It reflects a physical reality where individuality loses its sharpness. Another change appears in interaction rates. In calm regimes, particles interact occasionally. Collisions are discrete events separated by quiet intervals. In extreme fields, interaction becomes constant. Particles are continuously exchanging energy, momentum, and identity. Virtual particles appear and disappear at such a rate that the boundary between real and virtual becomes fuzzy. Processes that are normally rare become common. Pair creation accelerates. Annihilation events multiply. The vacuum behaves less like empty space and more like a turbulent medium filled with transient structure. This turbulence is not random chaos. It has statistical patterns. Certain configurations appear more often than others. Certain modes dominate, but the overall behavior is no longer smooth or easily predictable. Small disturbances can cascade into large effects. This cascading behavior is a hallmark of systems near criticality. As energy density rises, the system approaches a point where no single configuration is strongly preferred. Multiple outcomes compete. The system flickers between possibilities. Particles behave less like stable entities and more like momentary expressions of deeper interactions. Another sign of impolite behavior appears in the way forces act. At low energies, forces act cleanly. You can calculate how strongly particles repel or attract based on their charges and distances. At high energies, those calculations become scale-dependent. The effective strength of interactions changes with energy. Couplings run. What you thought was constant begins to drift. This running of interaction strengths is a well-known feature of quantum field theory, but near extreme conditions it becomes dramatic. The force between charges does not simply increase smoothly as distance decreases. Instead, it behaves unpredictably, sometimes strengthening, sometimes weakening depending on the interplay of fluctuations. This unpredictability undermines the idea of simple cause and effect. Add a bit more charge, and instead of a proportional response, you might trigger a qualitative change, a new instability, a burst of particle creation, a rearrangement of the field configuration. The system becomes sensitive in ways that defy intuition built from calmer regimes. Time itself begins to feel less orderly. Quantum mechanics already blurs the classical notion of time by allowing processes to occur probabilistically rather than deterministically. At extreme energy densities, this blur intensifies, timescales shorten, events overlap. The sequence of cause and effect becomes harder to disentangle. In such environments, it is no longer meaningful to say that one specific event caused another in a clean temporal order. Instead, processes occur in overlapping networks of influence, with feedback loops that fold back on themselves. Particles are no longer polite guests arriving, interacting and leaving. They are part of a restless crowd, constantly forming, dissolving and reforming in response to the collective state of the system. Another profound change involves stability. At low energies, particles like electrons are stable, they persist. They have well-defined lifetimes that exceed the age of the universe. At extreme energies, stability becomes conditional. Particles can decay, transform, or merge in ways that are normally forbidden or extremely rare. High-energy environments open new channels. Conservation laws still apply, but the space of allowed outcomes expands dramatically. Particles can borrow energy from the field, change identities, or appear briefly before disappearing again. This constant transformation makes it difficult to talk about particles as enduring objects. They become events rather than things, temporary patterns in an ever-shifting quantum field. This shift has deep implications for how charge itself is understood. Charge is tied to particles. If particles lose their individuality and stability, charge becomes less localized. It spreads across interactions. It becomes something shared rather than owned. In extreme regimes, charge may be better thought of as a property of the field configuration as a whole rather than of individual entities. This collective behavior is another sign that we are approaching a boundary where familiar categories break down. One of the most unsettling aspects of quantum behavior under extreme conditions is that intuition built from everyday probability fails. We are used to randomness averaging out. Flip enough coins, and patterns emerge. Noise smooths itself away. At high energy densities, noise can amplify instead. Fluctuations reinforce one another. Rare events become common. The system explores its space of possibilities aggressively, not gently. This exploration can lead to sudden transitions, bursts of activity, or the spontaneous formation of structure. From a distance, this might look like instability. From a deeper perspective, it is the system responding to stress by exploiting every available degree of freedom. Quantum mechanics provides those degrees of freedom in abundance. The vacuum itself becomes a participant. Its fluctuations are no longer background noise. They shape outcomes. They determine which configurations are accessible and which are suppressed. This participation of the vacuum is one of the clearest indicators that the polite classical picture has fully dissolved. At this point, it is no longer useful to imagine particles as tiny beads moving through space. They are excitations of fields. Those fields are embedded in spacetime. Spacetime itself is fluctuating. Everything is interacting with everything else. This interconnectedness makes precise prediction extraordinarily difficult. It also makes sharp limits elusive. Instead of a clear maximum charge, we encounter a region of behavior where the notion of adding more becomes ill-defined. Add more energy, and you do not simply increase charge density. You change the character of the system. You trigger new quantum effects that redistribute, transform, and blur what you're trying to control. This is why extreme charge configurations are so resistant to simple analysis. The system refuses to remain simple long enough for a single quantity to dominate. From a practical standpoint, this resistance protects the universe. If particles continued to behave politely under all conditions, if fluctuations remained small and controllable no matter how extreme the energy density, then nothing would prevent true infinities from forming. Fields could grow without bound, energy density could diverge, space-time could tear. Instead, quantum mechanics ensures that order gives way to restless complexity long before those extremes are reached. Particles misbehave precisely when misbehavior is needed. They fluctuate more. They interact more. They refuse to be pinned down. They spread charge and energy across many channels, diluting concentrations that would otherwise become pathological. This misbehavior is not a flaw. It is a feature. It is how the universe avoids letting any single quantity dominate absolutely. As we move closer to the Planck limit, these quantum tremors grow stronger. The ground beneath our concept shakes, definitions wobble, measurements blur. Particles cease to be polite not because they are rebellious, but because politeness is a luxury reserved for low-energy, low-density environments. At the deepest levels, reality is not orderly in the way we expect. It is dynamic, relational, and restless. Stability emerges only when conditions allow it. There is a comforting idea that empty space is exactly what it sounds like. Nothing. A quiet absence where matter and energy are simply not present. We picture it as a neutral backdrop, a blank page on which the universe writes its story. This intuition works well enough in daily life and even in much of classical physics. If you remove all the air from a container, you call it a vacuum and expect nothing interesting to happen inside. But at deeper levels, empty space has never truly been empty. Even under the calmest conditions, the vacuum is alive with activity. Quantum physics tells us that fields exist everywhere, even where there are no particles. These fields cannot sit perfectly still. They fluctuate. They ripple. They borrow energy briefly and give it back. Pairs of particles and antiparticles appear and vanish in time so short, they normally leave no trace behind. This restless behaviour is always present, but it usually remains hidden, averaged out, politely invisible. That politeness depends on conditions. As energy density rises, as fields grow stronger and charge crowds itself more tightly, the vacuum begins to change its demeanour. The background noise grows louder, fluctuations last longer. The boundary between what is real and what is virtual starts to blur, and eventually, empty space refuses to stay empty. This refusal is not dramatic in the way explosions are dramatic. It does not announce itself with a single catastrophic event. Instead, it unfolds gradually through subtle shifts in probability, stability, and behaviour. The vacuum becomes less of a backdrop and more of an active participant. One of the first signs of this change is that virtual particles stop behaving like polite guests. Under normal circumstances, virtual particle pairs appear briefly and annihilate almost immediately. They are allowed to exist only within the limits imposed by quantum uncertainty. They cannot be directly observed. They leave no lasting footprint. Strong electric fields alter that balance. When an electric field becomes intense enough, it can pull these virtual pairs apart faster than they can annihilate. The field does work on them. It supplies energy. The particles become real. What was once a fleeting fluctuation turns into a lasting presence. This process is sometimes described as the vacuum breaking down, but that phrasing can be misleading. Nothing is actually breaking. The vacuum is behaving exactly as quantum theory predicts. It is responding to stress by changing its state. What changes is the role the vacuum plays. Instead of merely hosting fields and particles, it begins to generate them. Instead of being a passive medium, it becomes a source. The stronger the field, the more prolific this creation becomes. Particle production accelerates. Energy is drained from the field and converted into matter and antimatter. This is not a rare or exotic effect reserved for theoretical speculation. Versions of it have been studied in laboratories, though far from the extreme conditions we're discussing. Even modestly strong fields can polarize the vacuum slightly, altering how charges interact. At much higher field strengths, the effect becomes undeniable. This behavior acts as a natural regulator. As charge crowds itself and energy density climbs, the vacuum responds by producing new charged particles. These particles screen the original field. They rearrange the charge distribution. They reduce the field's intensity locally. In doing so, they oppose further growth. But this opposition is not absolute. It is dynamic. The vacuum does not impose a hard cutoff where particle creation suddenly turns on and stops everything. Instead, it gradually increases its response. The stronger the field, the more aggressive the vacuum becomes in generating particles. It is a smooth, adaptive reaction rather than a rigid barrier. This smoothness is important because it means the system never reaches a simple breaking point. There is no single moment where you can say, "Now the vacuum fails." The transition is continuous, layered, and context-dependent. As energy density continues to rise, the behaviour of the vacuum grows more complex. Particle creation is no longer limited to simple pairs. Interactions between newly created particles generate cascades. Secondary processes emerge. The vacuum becomes a turbulent environment filled with transient structures. At this stage, the idea of empty space as a neutral container has completely dissolved. Space is doing things. Another subtle shift occurs in how stability is defined. In low-energy physics, the vacuum is assumed to be stable. It is the lowest energy state. Nothing can happen spontaneously without external input. At extreme field strengths, that assumption must be reconsidered. The vacuum becomes metastable. This means that while it may still be the lowest energy state globally, locally it can transition into excited configurations under sufficient stress. These configurations may persist for varying durations before relaxing back. During that time, the properties of space itself are altered. Fields propagate differently. Particles acquire effective masses. Interaction strengths shift. The vacuum's role as a constant background evaporates. This instability does not imply chaos. It implies responsiveness. The vacuum, under strain, explores alternative configurations that allow it to accommodate extreme conditions without collapsing into contradiction. It is flexible in ways classical intuition does not anticipate. As we approach even higher energy densities, approaching the Planck regime, the distinction between vacuum and field becomes increasingly artificial. The vacuum is defined by the absence of excitations of fields. But if the fields themselves are fluctuating violently, and spacetime geometry is also fluctuating, then the notion of a stable vacuum becomes ambiguous. What does empty mean when space itself is restless? This question is not philosophical decoration. It is a technical challenge at the heart of modern theoretical physics. Many approaches to quantum gravity suggest that the vacuum is not a single state, but a collection of possible states, each corresponding to different underlying structures. Under extreme conditions, the system may transition between these states. Such transitions would not look like particles popping in and out of space. They would look like changes in the fabric of reality itself. Distances, durations, and interactions would shift subtly but profoundly. In this view, vacuum instability is not just about particle creation. It is about the loss of a unique, well-defined background. Space stops being something you can subtract from the system to simplify analysis. It becomes inseparable from the dynamics. Charge plays a crucial role in driving this process because electric fields can concentrate energy efficiently. Unlike mass, which tends to clump slowly under gravity, electric fields can store enormous energy densities over relatively small regions. This makes them particularly effective at stressing the vacuum. As that stress increases, the vacuum responds not by remaining empty, but by restructuring itself. One way to understand this restructuring is to think of the vacuum as a medium with internal degrees of freedom. At low energies, those degrees of freedom are frozen out, they do nothing. At high energies, they become active. They absorb energy, redistribute it, and alter the effective laws governing the system. This activation spreads stress across more channels, reducing the burden on any single quantity. Charge does not get to crowd infinitely because the vacuum refuses to cooperate. Another important aspect of vacuum instability is that it undermines locality. In low-energy physics, events are local. You can say what happens at one point in space without worrying too much about distant regions. At high energies, especially when vacuum fluctuations become significant, this separation weakens. Correlations extend over larger distances. Events become entangled. Particle creation in one region can influence behavior elsewhere. The vacuum becomes a medium through which influence propagates in non-trivial ways. This non-local behavior further complicates attempts to define sharp limits. You cannot isolate a small region and talk about its charge density independently of its surroundings. The vacuum ties everything together. Time is affected as well. In unstable vacuum conditions, temporal order becomes fuzzy. Fluctuations occur on time scales comparable to the Planck time. Processes overlap. The idea of a sequence of events breaks down into a network of interactions without a single, preferred ordering. This temporal fuzziness means that even the concept of causality must be handled with care. Causes and effects blur into one another. Feedback loops become immediate rather than delayed. All of this makes the question, what happens when charge reaches the Planck limit, increasingly difficult to phrase. The vacuum's refusal to remain empty ensures that charge cannot be cleanly separated from its consequences. Attempting to push charge further simply activates more layers of response. From this perspective, vacuum instability is not a flaw in the universe, it is a stabilizing mechanism. It ensures that extreme energy densities trigger new behavior long before any mathematical infinity can be realized. It also hints at something deeper. If the vacuum can change its state under stress, then the laws we observe may be effective laws rather than absolute ones. They may depend on the vacuum configuration appropriate to the energy scale we inhabit. At everyday scales, we live in a vacuum that behaves calmly. Fields propagate predictably. Particles have stable properties. Space feels smooth. At extreme scales, the vacuum may behave very differently, supporting different effective laws. This idea appears in many areas of theoretical physics. It suggests that what we call constants may vary under extreme conditions, that symmetries may break or reassemble, that reality has layers, each revealed only when pushed hard enough. Vacuum instability is the gateway to those layers. It marks the point where empty space can no longer be ignored, where it asserts itself as an active, responsive component of the universe. It ensures that pushing charge toward ultimate limits does not result in runaway behavior, but in transformation. As the vacuum fills itself with particles, fluctuations, and altered geometry, the system becomes more complex, not less. Energy is redistributed, stress is diffused, definitions soften. This complexity may feel unsatisfying if one is searching for clean answers, but it is deeply consistent with how nature behaves everywhere else. Simplicity gives way to richness under pressure. Order emerges from interaction, not from rigidity. The vacuum, restless and responsive, stands between us and infinity, not as a barrier, but as a transformation zone where old concepts quietly dissolve and new ones begin to form. When gravity first enters the conversation about charge, it does so almost apologetically. For most of physics, gravity is the weakest voice in the room. Between charged particles, electromagnetic forces dominate so completely that gravity can be ignored without consequence. Two electrons repel each other with a force so much stronger than their mutual gravitational attraction that the comparison feels almost unfair. In everyday situations, gravity governs falling apples and orbiting planets, while charge governs atoms, chemistry, and technology. The two seem to live in separate worlds. That separation holds only as long as energy density remains modest. As charge crowds itself more tightly, and fields grow more intense, the energy stored in those fields becomes impossible to dismiss. Energy, regardless of its source, gravitates. This is not a poetic statement. It is a precise consequence of general relativity. Anything that carries energy and momentum contributes to the curvature of space-time. Electric fields are no exception. At low field strengths, the gravitational effect of an electric field is vanishingly small. You could surround an object with powerful electric fields and space-time would barely notice. But as energy density climbs, gravity stops whispering and starts speaking clearly enough to matter. This is where the story becomes quietly profound. Charge does not suddenly turn into gravity. The electric force does not weaken or transform into something else. Instead, gravity responds to the situation charge has created. It responds to the energy packed into space, to the stress placed on the geometry itself. Gravity does not care whether energy comes from mass, motion, radiation, or fields. It curves space-time all the same. As the electric field strengthens, space-time begins to curve inward around it. This curvature changes distances, alters time flow, and reshapes how fields propagate. What began as an electromagnetic problem becomes a geometric one. At first, this curvature is gentle. Calculations remain tractable. The field's gravitational influence can be treated as a small correction. But corrections accumulate. As charge continues to crowd itself, curvature grows. Time dilation becomes noticeable. Paths of particles bend more strongly. The environment the field lives in is no longer flat. This marks a shift from additive effects to feedback. The charge creates a field. The field stores energy. The energy curves space-time. Curved space-time affects how the field behaves. That altered behavior can further concentrate energy, deepening curvature. The system becomes self-referential. There is no longer a clean separation between source and response. This feedback loop is not explosive. It is subtle, persistent, and deeply constraining. At some point, the curvature becomes strong enough that it begins to trap energy rather than letting it disperse. Instead of spreading outward freely, field energy lingers. It orbits, circulates, and accumulates. The geometry itself encourages confinement. This is where black holes enter the conversation, not loudly, but as a quiet reference point. A black hole is not defined by what it contains, but by how space-time behaves around it. When curvature becomes strong enough, an event horizon forms. Beyond that horizon, paths through space-time lead inward inevitably. Information cannot escape. The system becomes causally isolated from the outside. In classical general relativity, black holes form when mass is compressed into a sufficiently small region. But mass is only one form of energy. In principle, any sufficiently concentrated energy density can produce similar effects. This raises a natural question. If electric fields can store enormous amounts of energy, could extreme charge configurations produce black hole-like behavior? The answer, according to theory, is yes, but not in the straightforward way one might imagine. As charge builds and energy density rises, space-time curvature increases. If the energy becomes concentrated within a region smaller than a certain critical size, an event horizon can form. This horizon would not care whether the energy came from mass or from an electric field. Gravity responds to energy alone. However, charge brings complications. Unlike mass, charge produces repulsion. Like charges push apart, this repulsion resists confinement. Gravity pulls inward, electromagnetism pushes outward. The balance between these forces determines what configurations are possible. In certain theoretical solutions to Einstein's equations, charged black holes exist. These objects carry both mass and electric charge. Their space-time structure differs from that of uncharged black holes. They have additional horizons. Their internal geometry is more complex. But there is an important constraint. There is a maximum amount of charge a black hole can carry relative to its mass. Beyond that, the equations no longer describe a black hole with a horizon. Instead, they describe a naked singularity, an exposed region of infinite curvature without a horizon. Most physicists believe naked singularities do not exist in nature, not because equations forbid them absolutely, but because deeper principles appear to prevent their formation. This belief is often summarized as the idea that nature hides its singularities behind horizons. This belief has consequences for extreme charge. If charge were allowed to crowd indefinitely, it could in principle overwhelm gravity's ability to confine it, leading to configurations with exposed infinities. The apparent absence of such configurations suggests that something intervenes before that happens, that something is the combined response of quantum mechanics, electromagnetism, and gravity. As charge density rises, quantum effects destabilize the vacuum. Particle creation occurs, energy redistributes. As energy concentrates further, space-time curvature increases. Time slows. Horizons threaten to form. Each effect resists unlimited growth in its own way. Rather than allowing charge to pile up unchecked, the system reorganizes. This reorganization can take many forms. Energy can be converted into particles that escape the region. Charge can be screened by newly created oppositely charged particles. Spacetime curvature can trap energy in ways that alter the system's evolution. In some cases, the system may indeed form a black hole, but that black hole will obey constraints. Its charge will be limited. Its horizon will regulate what can be observed. The formation of a horizon itself acts as a kind of censorship, preventing external observers from accessing regions where our descriptions fail completely. This is why black holes are such important reference points in discussions of ultimate limits. They are not endpoints, they are regulatory structures. They represent the universe's way of saying, beyond this, your questions must change. Inside a black hole, space-time behaves in ways we do not yet fully understand. Classical descriptions break down. Quantum gravity is required, but from the outside the system remains well behaved. Energy is conserved, charge is conserved. The horizon enforces consistency. In this sense, black holes are not failures of physics, they are boundaries between regimes. When extreme charge configurations approach conditions where gravity can no longer be ignored, black hole-like behavior becomes part of the landscape of possibilities, not necessarily as an inevitable outcome, but as a constraint shaping what configurations can exist stably. It is also worth noting that black holes themselves are not static. They interact with quantum effects, they emit radiation, they lose mass and charge over time. Even here, nothing remains frozen. A highly charged black hole will tend to lose its charge faster than its mass. Quantum processes near the horizon favour the emission of charged particles that reduce the black hole's net charge. This behaviour again points toward a preference for neutrality and stability. Charge, when coupled with gravity, finds it difficult to remain extreme for long. This difficulty is not imposed by a single rule. It emerges from the interplay of many effects. Electromagnetic repulsion resists confinement. Quantum mechanics introduces fluctuations and particle creation. Gravity reshapes space-time and enforces causal structure. Horizons regulate information flow. Together, these effects conspire to prevent charge from reaching a clean, unlimited extreme. The conversation with black holes is quiet because it does not end in spectacle. There is no sudden collapse the moment charge crosses a threshold. Instead, there is a gradual narrowing of possibilities. Certain configurations become unstable, others become inaccessible. The space of allowed states shrinks. As we push charge toward its ultimate boundary, we find ourselves guided, gently but firmly, towards structures that limit what can be observed and what can be defined. Black holes are one such structure. They are not the only one, but they are among the most instructive. They show us that gravity does not merely add another force to the mix, it changes the rules of the game. It introduces geometry as an active constraint. It ensures that extreme energy densities do not simply sit there as numbers, but reshape the arena itself. This reshaping has a calming effect on the system as a whole. By curving space-time, gravity slows processes, stretches time, and creates horizons that regulate behavior. What might otherwise race toward infinity is instead redirected into forms that preserve consistency. From this perspective, black holes are not monsters lurking at the edge of physics. They are mediators. They allow the universe to accommodate extreme conditions without tearing itself apart. As we continue, the role of gravity will remain central, because once gravity is involved, the question of limits becomes inseparable from the question of self-protection. How does the universe prevent any single interaction from dominating absolutely? How does it maintain coherence under stress? There is a temptation, when discussing ultimate limits, to imagine nature as a rule enforcer, as if somewhere deep in the machinery of reality there is a firm boundary, a sign that reads "no further," placed deliberately to stop us from going too far. It is an understandable impulse. we encounter limits everywhere in human-made systems. Batteries stop charging, engines overheat, materials snap. So when we hear about the Planck scale, it feels natural to ask whether nature itself intervenes, whether the universe actively prevents certain extremes from ever being reached. But the deeper you look, the clearer it becomes that nature does not intervene in the way a referee intervenes in a game. There is no external authority stepping in to halt the process. Instead, the system protects itself from within. The laws that govern it are structured in such a way that pushing toward an extreme does not lead to a forbidden state, but to a transformation of the situation itself. Self-protection, in this context, is not a conscious act. It is an emergent consequence of how the fundamental ingredients of reality interact. To see this, it helps to reflect on what we mean by the Planck limit in the first place. It is not a physical barrier you can collide with. It is a scale where several independent descriptions of reality begin to overlap. Quantum mechanics, which governs small things. Relativity, which governs energy and geometry. Field theory, which governs interactions. At everyday scales, these frameworks operate mostly independently. At the Planck scale, they collide. That collision is the source of what feels like intervention. When charge is pushed toward extreme concentration, several things happen at once. Energy density rises, quantum fluctuations grow, space-time curvature intensifies, the vacuum becomes unstable. None of these effects alone stops the process. Together, they radically alter the conditions under which the process is occurring. This alteration is the key. Nature does not say, "You may not exceed this value of charge." Instead, it says, "If you try to exceed this regime, the meaning of charge itself will change." The rules evolve in response to stress. The system protects coherence by refusing to let a single description dominate all the way to infinity. This kind of self-protection is common in complex systems. In materials science, when you apply stress to a solid, it behaves elastically at first. Remove the stress and it returns to its original shape. Increase the stress and it deforms plastically. Push further and it fractures. At no point does the material violate physical law. It simply transitions between regimes where different descriptions apply. The universe behaves similarly, but with more subtlety. As charge approaches extreme densities, the elastic regime ends. Linear approximations fail. New degrees of freedom become active. Particle creation begins, geometry responds, time dilates. Each response redistributes stress, preventing runaway behavior. This redistribution is not arbitrary. It follows from conservation laws, symmetries, and the fundamental structure of interactions. Consider energy conservation. Energy cannot disappear. If you keep injecting energy to crowd charge more tightly, that energy must go somewhere. At low densities it stays in the field. At higher densities the field becomes unstable and converts energy into particles. At even higher densities, space-time curvature stores energy geometrically. Each layer absorbs part of the burden. Consider charge conservation. Charge is conserved globally, but its local distribution can change dramatically. Creating particle-antiparticle pairs preserves total charge while allowing local screening. Extreme charge concentrations invite their own dilution through this mechanism. Consider causality. Information cannot propagate faster than light. As space-time curves and horizons form, regions become causally isolated. This isolation limits how configurations can evolve and how extremes can influence the rest of the universe. None of these principles were introduced to prevent infinities. They exist independently. Their combined effect, however, is to make infinities physically unreachable. This is what self-protection looks like at a fundamental level, not an added rule, but a convergence of existing ones. It is also worth noting that this self-protection is scale-dependent. At everyday scales, it is invisible. You can increase voltage, compress matter, accelerate particles, and nothing dramatic happens. The protective mechanisms remain dormant because the stress is low. As you push harder, the mechanisms awaken gradually, first quantum corrections, then vacuum polarization, then particle creation, then curvature. Each stage introduces new behavior that resists further concentration. This gradual activation is crucial. It ensures continuity. The universe does not snap from one regime to another abruptly. It eases the transition, allowing structures to persist and evolve rather than collapse into incoherence. From the outside, this can look like intervention. From the inside, it is simply response. Another way to see this is to consider the role of measurement. To say that charge has reached a certain extreme value assumes that the value can be meaningfully defined and measured. But near the Planck scale, measurement itself becomes problematic. To localize charge, you need probes with extremely high energy. Those probes disturb spacetime, they create curvature, they trigger fluctuations. At some point, the act of measurement injects as much uncertainty as information. The question how much charge is here no longer has a sharp answer. The system protects itself by making the question ill-posed. This is not obstruction, it is coherence. If the universe allowed sharply defined, infinitely large values of physical quantities, it would undermine its own predictability. Laws would lose meaning. Cause and effect would dissolve. Structure would be impossible to sustain. Instead, nature ensures that extreme questions soften before they break anything. This softness is often mistaken for ignorance. We say we do not know what happens beyond the Planck scale, but it is more accurate to say that our current concepts do not survive unchanged beyond it. The universe does not hide answers, it reshapes the questions. This reshaping is evident in many speculative approaches to quantum gravity. Some suggest space-time becomes discrete, composed of fundamental units that cannot be subdivided further. Others suggest space-time emerges from networks of relationships rather than existing as a background. Others propose that geometry and matter are two aspects of the same underlying structure. Despite their differences, these ideas share a common theme. They all replace unbounded quantities with relational structures. Instead of infinite density, you get finite connectivity. Instead of infinite curvature, you get bounded configurations. Instead of runaway charge, you get reorganized interactions. These are not arbitrary choices. They are guided by the requirement that the theory remain internally consistent. Self-protection, then, is not an extra feature bolted onto physics. It is the natural outcome of consistency. Charge pushing toward the Planck limit threatens consistency because it tries to isolate one aspect of reality and let it dominate. The universe responds by refusing to let isolation persist. It entangles charge with vacuum, with geometry, with quantum structure, until no single quantity can be pushed independently of the rest. This entanglement is the deepest form of protection. It ensures that extreme conditions do not lead to singular, uncontrollable behavior, but to richer, more interconnected dynamics. The price of pushing harder is complexity, not collapse. There is also an aesthetic aspect to this, though it is not merely aesthetic. The universe appears to favour balance over absolutes. Extremes are permitted, but only in ways that preserve overall harmony. Charge can become enormous, but only if gravity, quantum effects, and geometry are allowed to respond. In this sense, the Planck limit is not a forbidden zone. It is a negotiation zone, a place where different aspects of reality assert their relevance and none is allowed to dominate completely. This negotiation is ongoing. It is not resolved by a single mechanism. It unfolds differently depending on context, configuration, and scale. That is why there is no single answer to what happens when charge reaches the Planck limit. There is a family of behaviours, all guided by the same principle of self-consistency. This principle also explains why extreme conditions are so rare in the observable universe, not because they are prohibited, but because they are difficult to sustain. The moment they begin to form, they activate responses that redistribute energy and smooth out imbalances. Stars regulate themselves through pressure and radiation. Galaxies regulate themselves through feedback and expansion. Black holes regulate themselves through horizons and radiation. Extreme charge configurations would be no different. Nature does not intervene like an external authority. It intervenes like a living system maintaining homeostasis. Push too hard in one direction, and compensatory processes arise. This analogy should not be taken too literally. The universe is not alive in a biological sense, but the pattern is real. Stability emerges from interaction, not from prohibition. As we approach the Planck scale, this pattern reaches its most profound expression. The very fabric of reality participates in the regulation. Space, time, matter, and fields all respond together. The result is not a clean boundary, but a softening of extremes. From our perspective, this feels like a mystery. From the universe's perspective, it is simply how things fit together. And this brings us to a subtle but important realization. The question of whether nature intervenes assumes a separation between the laws of physics and the situations they govern, as if the laws exist independently and then step in when needed. In reality, the laws are the behavior. Nature does not intervene because nature is not separate from its rules. The rules are the patterns that emerge when everything interacts. Self-protection is just one of those patterns. Understanding this reframes how we think about limits. Limits are not fences, they are transitions. They mark where one pattern gives way to another. As charge approaches the Planck limit, the pattern of charge as a localizable quantity in smooth space-time gives way to a different pattern, one where charge, space, and energy are inseparable aspects of a deeper structure. Nothing stops, nothing breaks, nothing explodes by default. The universe simply refuses to let us keep asking the same question in the same way. And that refusal, gentle and persistent, is perhaps the most elegant form of self-protection imaginable. There is a natural follow-up question that quietly arises once we accept that extreme charge triggers layer upon layer of response. If the universe allows charge to build, if nothing explicitly forbids pushing toward the deepest limits, then why have we never seen it? Not in laboratories, not in astrophysical observations, not in the aftermath of cosmic events that dwarf anything humans could engineer. Why does ultimate charge remain hidden, spoken of only in equations and thought experiments never encountered directly? The answer is not that it does not occur, it is that it does not reveal itself in the way our instincts expect. What stands between us and ultimate charge is not a single barrier, but a veil. A collection of effects that obscure, transform, and redirect extreme conditions before they can present themselves as a clean, observable object. This veil is not designed. It is woven naturally from the same interactions that govern everything else. To understand why we never see ultimate charge, we need to understand how observation itself works. Observation is interaction. To see something, to measure it, to detect it in any way, we must exchange energy or information with it. Light must scatter, particles must collide, fields must couple. This exchange is usually gentle. It barely disturbs the system being observed. But as conditions become extreme, the act of observation becomes intrusive. At very high energy densities, there is no such thing as a passive measurement. If a region of space were approaching extreme charge concentration, any attempt to probe it would inject additional energy. That energy would not simply bounce back as data. It would alter the region itself. It would contribute to curvature, trigger fluctuations, and activate the same protective responses already at play. In this way, ultimate charge hides not by being distant, but by being reactive. The closer you get, the more the system changes in response to your presence. This is not concealment in a conspiratorial sense. It is a natural consequence of coupling between observer and observed at fundamental scales. This coupling alone would make direct observation difficult. But it is only the first layer of the veil. Another layer comes from instability. Extreme charge configurations are not static objects sitting around waiting to be noticed. They are dynamic, short-lived, and highly sensitive. The moment charge density rises too far, it activates processes that dissipate or redistribute it. Particle creation, screening, field fragmentation, curvature effects. Each of these acts on timescales that shrink as energy density rises. By the time a configuration becomes extreme enough to approach ultimate limits, it is already in the process of changing. From the outside, this looks like absence. From the inside, it is constant activity. There is no stable snapshot to capture because the system does not remain in one configuration long enough. This is similar to why we never see isolated temperature singularities or perfectly rigid materials. The moment conditions approach such extremes, the system reorganizes. What we observe instead are the products of that reorganization, not the unattainable limit itself. The universe does not display its edges. It shows us the transitions that prevent those edges from forming. Astrophysics provides a clear example of this veiling effect. The most extreme environments we know of involve compact objects like neutron stars and black holes. These objects concentrate mass and energy far beyond anything achievable on Earth. If ultimate charge were something that could exist openly, these would be the places to find it. Yet even there, charge remains modest. Neutron stars are extraordinarily dense, but they are nearly electrically neutral. Any excess charge quickly attracts opposite charge from the surrounding environment, or is expelled by intense electric fields. Black holes, which can in principle carry charge, are observed to be almost neutral as well. If they acquire charge, they tend to lose it rapidly through quantum processes. This is not because the universe dislikes charge, it is because charge creates forces that make isolation difficult. Gravity attracts indiscriminately. Charge repels selectively. In a dense environment, repulsion is efficient at undoing accumulation. Any attempt to maintain extreme charge draws in compensating effects that neutralize it. This dynamic neutrality is another strand of the veil. Even when enormous energies are present, charge does not get to stand alone. It is always accompanied by processes that counterbalance it. Those processes are efficient precisely when conditions become extreme. There is also a geometric aspect to the veil. As we've seen, extreme energy densities curve spacetime. Curvature introduces horizons, redshifts, and time dilation. These effects limit what information can escape a region and how it is perceived by distant observers. If a region were to approach a state dominated by extreme charge, space-time around it would respond. Time would slow, signals would stretch. From the outside, the region would appear frozen, dimmed, or inaccessible. This is not speculation. It happens near black holes. Objects falling toward an event horizon never appear to cross it from the perspective of a distant observer. Their signals become weaker and slower until they fade from view. If ultimate charge configurations produce similar curvature effects, then they would naturally hide themselves from observation. Not because they are forbidden, but because space-time itself limits our access. This geometric veiling ensures that even if such conditions briefly exist, they do not present themselves as observable objects with clear properties. They become regions of altered causal structure, partially or fully cut off from the rest of the universe. Another layer of the veil lies in how information is processed. At everyday scales, we describe systems using a small number of variables: position, momentum, charge, energy. At extreme scales, the number of relevant degrees of freedom explodes. Fields fluctuate, geometry changes, particles appear and disappear. Information becomes highly distributed. From an observational standpoint, this distribution acts like noise. Signals from an extreme region are not clean. They are scrambled by interactions, redshifts, and fluctuations. Extracting a simple quantity like how much charge is there becomes impossible because there is no single channel carrying that information intact. Instead, information leaks out in fragmented, degraded forms. Radiation spectra, particle emissions, gravitational effects. Each carries partial data, but none provides a complete picture. This fragmentation is not accidental. It is another manifestation of self-protection. Concentrated information, like concentrated energy, is unstable. The universe prefers information to be spread out. As charge approaches ultimate limits, the information required to describe it becomes similarly spread across many degrees of freedom. No single measurement captures it. No single observation reveals it. This is why theoretical discussions of ultimate charge rely on indirect reasoning. We infer limits from consistency, not from direct detection. We study how equations behave. We examine how known systems respond under stress. We look for contradictions and how they are resolved. The absence of direct observation is not a failure of technology. It is a feature of how extreme regimes behave. There is also a temporal veil to consider. Extreme charge configurations, if they form at all, likely exist only for extremely brief intervals. Timescales near the Planck time are unimaginably short. Processes unfold faster than any signal can propagate outward in an orderly way. Even if a configuration momentarily approached an ultimate boundary, it would dissolve into other forms almost immediately. Particle creation, radiation, curvature-driven restructuring. The system would move on before anything resembling a stable object could emerge. From our perspective, this looks like nothing happened. In reality, everything happened too fast and too locally for us to register it. This temporal brevity is not unique to charge. It appears in high-energy particle collisions. Short-lived states form and decay before they can be observed directly. We infer their existence from decay products, not from direct detection. At the Planck scale, this effect becomes overwhelming. There is no time for observation to keep up. Another subtle aspect of the veil comes from scale separation. Human observation, even aided by instruments, operates across a limited range of scales. We are good at macroscopic phenomena and increasingly good at microscopic ones, but the Planck scale lies far beyond both. Bridging that gap requires extrapolation. Extrapolation works only when behavior is smooth across scales. Near ultimate limits, behavior is not smooth. It changes character. New effects dominate. Old patterns dissolve. This lack of smoothness makes it impossible to infer ultimate behavior reliably from lower energy observations alone. It also means that even if ultimate charge influences observable phenomena indirectly, its signature is diluted, blended into many overlapping effects. The veil is thickest, not because the universe is hiding something, but because the transition itself is messy. This messiness is often misunderstood as mystery for its own sake. But it is simply the natural outcome of many interacting systems reaching their limits simultaneously. Electromagnetism, quantum mechanics, and gravity all assert themselves. None yields cleanly. The result is complexity. Complexity is difficult to observe cleanly. We see this even in far simpler systems. Turbulent fluids resist simple measurement. Complex ecosystems defy reduction to single variables. The more interactions matter, the harder it becomes to isolate causes. Ultimate charge lives at the extreme end of this spectrum. There is also a conceptual veil. To recognize something, we need a concept that applies. We need to know what we are looking for. Near the Planck limit, the concepts themselves fail. Charge ceases to be a well-defined local quantity. Space ceases to be a smooth background. Time ceases to flow uniformly. Without stable concepts, observation loses meaning. You cannot see what you cannot define. This is perhaps the deepest reason we never see ultimate charge. It is not merely hidden. It is undefined in the terms required for seeing. The universe does not present ultimate limits as objects. It presents them as transitions where our language must change. Every time physics has advanced, it has done so by recognizing such transitions. Classical mechanics failed at small scales, giving way to quantum mechanics. Newtonian gravity failed at high energies, giving way to relativity. Each failure was not an absence, but a signal that new descriptions were needed. Ultimate charge represents a similar boundary. We never see it because seeing it would require a framework that can describe it. That framework likely involves quantum gravity, a theory not yet complete. Until such a framework exists, ultimate charge remains an inferred boundary rather than an observable state. Even then, it may remain veiled, not by ignorance, but by principle. Some aspects of reality may be inherently relational rather than object-like. They may not appear as things to be seen, but as constraints on how things behave. Ultimate charge may be one of those aspects, a limit encoded in structure rather than displayed as an entity. This idea can feel unsatisfying. We like tangible extremes. We like edges we can point to. But the universe does not always cooperate with that preference. Instead, it offers guidance through absence. The fact that we never observe unlimited charge is itself a data point. It tells us that the universe has mechanisms that prevent such observations. By studying those mechanisms, we learn more than we would by witnessing the extreme itself. In this way, the veil is informative. It tells us that extreme charge is not something that exists openly in space-time. It is something approached asymptotically, redirected by response, hidden by transformation. The universe does not show us its most extreme states directly. It shows us how it avoids them. As we continue, this realization leads to a deeper question. If ultimate charge is never seen as an object, what does its existence tell us about reality? What does a limit that manifests as a veil rather than a wall say about the nature of physical law? When we step back from mechanisms, equations, and specific processes, a quieter question begins to surface. It is not about charge alone, or even about the Planck scale in isolation. It is about what limits like this reveal about the nature of reality itself. Not as a collection of objects, but as a structure. Not as a set of rules imposed from outside, but as patterns that arise from within. The existence of an ultimate boundary for charge, one that we never see directly and never cross cleanly, tells us something fundamental. It tells us that reality is not built to accommodate absolutes in the way our abstractions are. Mathematics is comfortable with infinities. Human language is comfortable with superlatives. The universe is not. Instead of allowing quantities to grow without bound, reality responds by changing the context in which those quantities exist. That response is consistent across domains. Speed does not exceed the speed of light. Density does not increase indefinitely without triggering new behavior. Temperature does not climb endlessly without unlocking new degrees of freedom. Charge does not crowd itself arbitrarily without activating vacuum, geometry, and quantum structure. This consistency suggests that limits are not accidents or special cases. They are structural features. One way to interpret this is that reality is relational rather than absolute. Physical quantities do not exist in isolation. They exist only in relation to other quantities, other structures, other scales. Charge has meaning because of fields. Fields have meaning because of space and time. Space and time have meaning because of how energy and information propagate. When any one of these is pushed too far, the relationships tighten. Independence disappears. The system insists on being treated as a whole. This insistence is one of the most important lessons of fundamental physics. It runs counter to our everyday intuition, which is built around separability. We are used to isolating systems, controlling variables, and treating influences as additive. That approach works remarkably well at human scales. It fails at extremes. The Planck limit is where separability collapses completely. At that boundary, you cannot talk about charge without talking about energy. You cannot talk about energy without talking about space-time. You cannot talk about space-time without talking about quantum uncertainty. Every attempt to isolate one aspect of reality immediately entangles it with the others. This entanglement is not just a feature of quantum mechanics in the narrow sense. It is a broader principle. The deeper you probe, the less reality allows itself to be partitioned into independent parts. This has profound implications for how we think about what is fundamental. For a long time, physics saw ultimate building blocks, smallest particles, most basic forces, final equations. The assumption was that if we could identify the pieces, the whole would be understood as their sum. Limits like the Planck scale challenge that assumption. They suggest that what is fundamental may not be pieces but relationships, not objects but constraints, not substances but patterns of interaction that cannot be reduced further without losing meaning. Charge, in this view, is not a thing that exists independently and then interacts. It is a way that certain degrees of freedom relate to one another within a particular regime. Push beyond that regime, and the description changes. This is why ultimate charge does not appear as an observable object. It is not an object. It is a boundary condition on how descriptions work. Another lesson embedded in this limit is that reality appears to be self-consistent before it is extreme. Whenever a quantity threatens to diverge, the system reorganizes to preserve consistency. Energy is redistributed. New channels open. Geometry responds. Definitions soften. The universe does not optimize for simplicity or extremity. It optimizes for coherence. This coherence is not imposed. It emerges. The laws of physics do not sit above reality enforcing order. They are descriptions of the order that emerges when everything interacts according to its nature. Limits arise because unconstrained extremes would undermine that order. An infinite charge density would dominate all interactions. An infinite energy density would destroy causal structure. An infinite curvature would make spacetime meaningless. None of these are compatible with a universe that contains structure, persistence, or observers. The fact that such infinities do not manifest physically tells us that reality is tuned, not in the sense of fine-tuning for life, but in the sense of internal balance. Extremes are allowed only insofar as they do not erase the possibility of structure altogether. This balance is subtle. Reality allows black holes, but hides their singularities. It allows quantum fluctuations, but averages them into stability. It allows enormous energies, but distributes them across geometry and fields. It allows charge, but resists its isolation. From this perspective, the Planck limit is not a failure of physics. It is evidence that physics is layered. Each layer has its own effective rules, its own valid questions, its own useful concepts. Problems arise when we try to extend a concept beyond the layer where it applies. Charge is a powerful concept at low and moderate energies. It becomes less useful as energy density rises. At the deepest level, it may not be fundamental at all. This idea is uncomfortable because it undermines the notion of a final, simple answer. It suggests that reality may not terminate in a single, elegant formula that explains everything in isolation. Instead, it may consist of a network of mutually supporting descriptions, each valid in its own domain. The Planck limit tells us that asking what is the maximum charge may be the wrong kind of question. It assumes that charge remains a well-defined quantity all the way down. The universe responds by showing us where that assumption fails. This failure is not arbitrary. It happens precisely when continuing to treat charge as an independent variable would conflict with other aspects of reality. In that sense, limits are not boundaries of existence. They are boundaries of language. They mark where the words and concepts we are using stop matching the structure they are meant to describe. Beyond those points, new language is required. This is why the Planck scale is so closely associated with the search for quantum gravity. Not because gravity suddenly becomes stronger than everything else, but because geometry becomes inseparable from quantum behavior. The very notion of spacetime, which underlies all physical quantities, comes into question. If spacetime itself is emergent, then any quantity defined within spacetime, including charge, is also emergent. Ultimate limits then reflect the breakdown of emergent descriptions, not the breakdown of reality. Reality itself continues. Our descriptions do not. Another implication of this limit concerns observation and knowledge. We often assume that with enough technology, enough ingenuity and enough time, any physical question can be answered empirically. Limits like this suggest otherwise. They suggest that some questions may be undecidable not because of ignorance, but because of principle. If reaching an extreme inevitably changes the system in ways that erase the meaning of the quantity you are trying to measure, then direct knowledge of that extreme is inaccessible, not hidden, but undefined. This does not mean the universe is unknowable. It means knowledge has a structure. There are things we can know precisely, things we can know approximately, and things we can only infer indirectly. Ultimate charge falls into the last category. We know it exists as a boundary because our theories demand consistency. We know what happens as we approach it because we see the warning signs. We know why we never see it because the mechanisms that protect coherence are visible at lower scales. But we do not know what it is in the way we know what an electron is or what a field is. And that may not be a deficiency. It may be a reflection of the fact that reality is not built from ultimate objects, but from processes and constraints. There is also a philosophical humility embedded in this realization. Human intuition is shaped by scales far removed from the Planck regime. We evolved to navigate a world of moderate energies, stable objects, and slow changes. It is unsurprising that our instincts struggle at extremes. What is remarkable is not that limits exist, but that we can infer them at all. That the universe is structured in such a way that pushing our theories reveals where they must change, rather than simply failing catastrophically. This suggests a deep compatibility between human reasoning and the structure of reality, not a perfect match, but a workable one. We can follow the trail of inconsistencies, divergences, and breakdowns, and use them as guides toward deeper understanding. The Planck limit in this sense is not a dead end. It is a signpost. It tells us that reality is layered, relational, and self-consistent. It tells us that extremes are not destinations but transitions. It tells us that what we experience as fundamental may be contingent on scale. It also tells us something about our role as observers. We are not external to the universe. We are part of it. Any attempt to probe its deepest limits necessarily involves us in the process. Measurement injects energy. Observation alters conditions. Knowledge comes at a cost. The fact that ultimate charge is veiled rather than displayed reminds us that there are limits to detachment. We cannot stand outside reality and inspect it from a neutral vantage point. We always interact from within. This does not diminish science. It grounds it. Science becomes not the search for final answers carved in stone, but the exploration of how descriptions change as we move across scales. It becomes an exercise in understanding when questions are well posed and when they are not. From that perspective, the most valuable information is often negative. Not what happens, but what cannot happen. Not what we see, but what we never see and why. The absence of ultimate charge as an observable phenomenon is one of those negative facts. It tells us that reality prioritizes coherence over extremity, that it enforces balance through transformation rather than prohibition. In a universe like this, limits are not enemies of understanding. They are guides. They tell us where to stop using one language and start developing another. They tell us which intuitions to trust and which to set aside. They tell us that the deepest structure of reality may not resemble the surface patterns we are familiar with. What stands out most clearly is not a single mechanism or a single conclusion, but a recurring theme. Whenever we push toward an ultimate boundary, the universe responds by weaving connections more tightly, by refusing to let any one quantity dominate, by preserving the conditions necessary for structure and meaning to exist at all. Charge reaches its limit not by hitting a wall, but by dissolving into a richer description of reality. That dissolution is not loss, it is transformation. And in that transformation, we glimpse something profound, not just about electricity or quantum fields or gravity, but about the kind of universe we inhabit, one that is resilient, relational, and quietly resistant to absolutes. There is a particular feeling that comes from standing near an edge without stepping over it. Not a sharp edge or a dangerous one, but a conceptual edge. A place where understanding stretches as far as it can, then grows quiet. That is where we are now. Not at a conclusion, not at an answer that closes anything off, but at a moment where the questions soften enough to let go of them. We began with charge as something familiar, a small shock, a current in a wire, a force that pushes and pulls in predictable ways. Along the way, that familiarity slowly loosened. Charge became crowded, fields strained, space responded. The vacuum refused to stay passive. Gravity joined in, not loudly, but inevitably. Each step added complexity, not confusion, revealing that what felt like a simple quantity was always part of something larger. Now, standing gently at this edge, it becomes clear that the most important lesson was never about a specific number or a precise limit. It was about behavior, about how reality responds when pushed, about the patterns that appear not when things are calm, but when they are stressed. One of those patterns is restraint, though not the kind enforced by barriers or rules shouted from on high. It is a quiet restraint, a tendency for extremes to invite their own transformation. Charge does not stop because it is forbidden. It stops being what it was because the conditions that made it meaningful no longer apply. That distinction matters. It means that the universe does not operate like a machine with hard-coded maximums. It operates like a system that adapts. When one variable begins to dominate, others respond. When energy concentrates, space bends. When fields intensify, the vacuum activates. When definitions strain, they blur rather than snap. This adaptive behavior is easy to miss if we focus only on endpoints. If we keep asking, what is the maximum? We overlook the more interesting question, which is, what happens as we approach? The answer to that second question is where the real insight lives. As charge is pushed toward its deepest boundary, nothing dramatic announces the moment. There is no cosmic alarm, no sudden failure. Instead, there is a gradual shift in how the system behaves. Responses overlap, interactions entangle. Simple descriptions give way to layered ones. That layering is not a flaw, it is a signature. It tells us that reality is not built from isolated pieces stacked on top of one another. It is built from relationships that tighten under pressure. At low energies, those relationships are loose enough that we can ignore many of them. At high energies, they assert themselves. This same pattern appears everywhere we look, once we know how to see it. Fluids become turbulent, materials yield, ecosystems reorganize. Even human thoughts, when pushed too hard, stop following linear paths and begin looping, associating and reframing. Stress reveals structure. At the Planck scale, stress reveals the deepest structure of all. It reveals that space is not merely where things happen, but part of what happens. That time is not just a backdrop for events, but a participant shaped by energy and motion. That empty space is not empty, but full of potential responses waiting to be activated. Charge, within this picture, becomes less like a substance and more like a question the universe asks itself. How should influence be distributed? How should energy flow? How should interactions remain consistent when everything is pushed to its limit? The universe answers not with a single mechanism, but with many working together. That cooperation is perhaps the most striking thing of all. There is no one force responsible for maintaining balance. Electromagnetism does its part. Quantum mechanics does its part. Gravity does its part. None dominates completely. Each constrains the others. This mutual constraint is what keeps reality from tearing itself apart. If electromagnetism alone ruled, charge could crowd infinitely. If gravity alone ruled, everything would collapse. If quantum mechanics alone ruled, nothing would settle into stable structures. It is only through their coexistence that a coherent universe emerges. This coexistence is not static, It is dynamic. It adapts to scale. At the scales of atoms and molecules, one balance holds. At the scales of stars and galaxies, another holds. At the scales approaching the Planck regime, yet another balance begins to form, one we are still learning how to describe. The fact that we cannot yet describe it fully is not discouraging. It is expected. Every time physics has encountered a boundary like this, progress has come not from forcing old ideas further, but from allowing new ones to emerge. Newtonian mechanics gave way to relativity. Classical fields gave way to quantum fields. Each transition preserved what worked, while letting go of what no longer fit. Letting go is part of understanding. That is why this edge does not feel like a stopping point. It feels like a pause, a place to rest before continuing in a different direction. We have followed charge as far as it makes sense to follow it using familiar language. Beyond this, the path continues, but the scenery changes, and that is okay. There is a quiet comfort in recognizing that not everything needs to be resolved tonight. Some questions are better left open, not because they are unimportant, but because their openness is what keeps inquiry alive. The universe, after all, is not in a hurry to finish explaining itself. It unfolds. It evolves. It reveals layers gradually, often only when conditions demand it. We, as observers, catch glimpses where we can, infer where we must, and accept that some aspects of reality are not objects to be grasped, but processes to be approached gently. Ultimate charge is one of those aspects. We never see it directly, not because it is hidden from us maliciously, but because it is not something that exists as a thing. It is a limit that expresses itself through behavior, through resistance, through transformation. Understanding that changes how we relate to limits in general. Limits stop feeling like failures or disappointments. They start feeling like guides. They tell us where our current language is strong and where it needs to change. They tell us when to stop pushing and start listening. There is also something quietly reassuring about this. It suggests that reality is not fragile. It does not shatter when pushed. It bends, adapts, and reorganizes. Even at its most extreme edges, it remains coherent, not because it enforces simplicity, but because it allows complexity to grow where needed. That coherence is what allows anything at all to exist. Stars, atoms, thoughts, questions asked in the quiet moments before sleep. In that sense, the Planck limit is not distant from us. It is connected through many layers to the same principles that keep everyday reality stable and intelligible. When you feel a static shock, when you watch lightning split the sky, when you plug in a device and trust it to work, you're interacting with systems that already embody these balancing acts just at gentler scales. The extreme cases differ in magnitude, not in spirit. So standing here, at this conceptual edge, there is nothing that needs to be forced, no final claim to make, no dramatic conclusion to draw. The picture is already complete enough to rest in, even if it remains unfinished. Charge reaches its ultimate boundary not by arriving somewhere, but by changing what arrival would mean. Space responds, time responds, the vacuum responds, reality responds. And then, quietly, the question dissolves into a broader understanding of how the universe maintains itself. That understanding does not demand attention. It does not require effort. It can simply sit in the background, like a thought that no longer needs to be chased. You do not have to hold on to it. It is enough to know that the universe has ways of keeping itself whole, even when pushed to its deepest edges. That extremes are met not with collapse but with transformation. That limits exist not to stop curiosity, but to redirect it. From here, the mind does not need to push further. It can ease back, letting the details fade while the pattern remains, the sense that there is more, always more, but that it will wait. And in that waiting, there is space to rest,